When we hear that the universe is expanding, our brains jump to a picture that works for everything we've ever seen. If something grows, it must be growing something else. A balloon expands into the surrounding air. A rising loaf of bread pushes into the space around the bowl. Even crowds expand by spilling into nearby streets. So it feels natural to imagine the universe pushing outward into some enormous emptiness that sits outside everything. But the word universe doesn't work that way. In cosmology, the universe isn't a bubble floating in a bigger space. It is space. It's the totality of distances, geometry, and time itself. And once you treat it that way, the whole question, what is it expanding into, turns out to be trickier than it seems, because the usual rules of growing objects don't apply when space itself is the thing that's changing. The surprising part is this: the expansion we talk about isn't a stretching toward an external void. It's a change in the distances between things within the universe. There's no outer shell, no edge, no empty container waiting to be filled. Just space-time evolving, according to the laws of gravity. Of course, that answer raises new questions. If there's no outside, how can distances grow? How do astronomers know space is stretching at all? And if the universe doesn't expand into anywhere, what does it mean for it to have been smaller in the past? That's where we're headed. When people first hear that the universe is expanding, the mental picture that pops up is almost always something like a balloon, a bubble, or a cloud of debris spreading through a larger room. That image is so powerful because it matches every kind of expansion we ever witness in daily life. If you pour water onto a table, the puddle expands outward into the surrounding dry surface. If a city grows, its borders stretch into farmland. Even when we talk about ideas spreading, we picture them moving through some mental space. In every case, growth has a background it pushes into. That background is passive and already exists before the expansion begins. This habit of thinking is so automatic that it's hard to imagine anything else. When scientists say the universe itself is expanding, most people swap in the closest analogy their brains have. The universe must be a thing, and this thing must be growing into a bigger thing. And then all the follow-up questions spill out. What's beyond the universe? How can something grow if it has nowhere to go? Did the outside exist before the Big Bang? Is it some vast empty void? Is it another dimension? Is it something we just haven't discovered yet? What makes this tricky is that these questions feel completely reasonable because they're built on the logic of everyday objects. But the universe is not an object moving through a larger container. It doesn't sit somewhere. There isn't a direction called outside. When cosmologists talk about expansion, they're not describing a physical shell ballooning outward. They're describing a change in how space behaves internally, how distances measured within the universe evolve over time. That idea is so far removed from everyday experience that people almost always reach for something familiar to anchor it. Some imagine the universe as a sphere. Others picture it as a fireball growing inside darkness. Still others think of it as a network of galaxies drifting apart into some greater emptiness. These aren't silly interpretations. They're normal attempts to translate a concept that has no direct analogy in our lives. But each of them carries hidden assumptions that turn out to be wrong the moment you bring in what we know from modern cosmology. One reason the intuitive picture fails is that objects in our world expand because they have internal pressure or added material. A balloon fills with air, bread dough fills with gas, crowds fill with people. The universe doesn't operate that way. Space doesn't need extra stuff to expand. It doesn't need an external void to move into. It doesn't even need a boundary that inches outward. What physicists call expansion is baked into the geometry of space-time itself. The distances between large-scale structures grow not because galaxies push outward, but because the metric, the mathematical rule that measures distance, changes as the universe evolves. Before diving deep into the physics, it helps to understand why the "into what" question is so hard to shake. Humans evolved to navigate local environments, rooms, landscapes, objects, and other people. We sense distances. We track motion. We instinctively expect boundaries, edges, and containers. When we think about the universe, we borrow the same mental software. We picture an edge because everything we've ever seen has boundaries. We imagine an outside because every boundary we've ever encountered separates an inside from something beyond it. And we expect that growth means traveling outward because that's how all physical motion works at our scale. This mindset made perfect sense for thousands of years, and it's still our starting point. But it becomes unreliable when applied to the cosmos. Space isn't like a balloon skin. There's no membrane and there's no external void pressing back on it. Space is an ingredient of the universe itself, and its behavior is governed by general relativity, not common sense. The mathematical description clearly shows that the universe can expand without needing an exterior. But turning that into intuition takes more than a formula. It takes untangling deep-seated assumptions most people don't even notice they're making. Another part of the confusion comes from the phrase, "the universe was smaller in the past." It sounds like a literal shrinking object that once took up less room. If something was smaller, it must have been inside something larger, and if it's bigger now, it must have pushed outward. But when cosmologists say the universe was smaller, they're referring to the distances between points within the universe, not the overall size thought of as a container. Think of it this way. If every distance in your city doubled overnight, every street, every block, every gap between houses, the city would be bigger. But it wouldn't expand into new countryside. The distances changed, not the territory it sits in. With the universe, there is no countryside at all. There's only the network of distances itself. Even though this sounds abstract, the idea has practical consequences. It shapes how astronomers interpret redshifts from distant galaxies. It affects how we understand cosmic time. It tells us whether the universe has a center. It even influences how we think about the Big Bang. Many people imagine the Big Bang as an explosion that occurred somewhere within a larger void. But the Big Bang wasn't an explosion in space. It was an event that happened everywhere at once because space itself was the thing coming into being and changing. There was no pre-existing space for anything to explode inside. The reason this discussion matters is because it sets the stage for everything that comes later. If we don't clear out the everyday assumptions right at the start, the rest of cosmology sounds like a bunch of paradoxes. People hear the universe has no edge and picture a borderless object floating somewhere, which leads right back to the same question. Floating in what? They hear space is expanding and imagine a physical substance stretching outward, which again leads to what's outside it. They hear the universe might be infinite and instantly imagine an infinite object suspended in an even larger infinite background. Every one of these mental traps is rooted in the same basic issue. Our intuition is shaped by objects inside space, not by space itself. When the thing you're trying to understand is space, everyday logic misfires. A good way to approach this is to briefly look at how we handle measurements. On Earth, distance is straightforward. You stretch a tape measure between 2 points. In cosmology, that tape measure changes over time. That doesn't mean someone is pulling on it. It means the geometry underlying the measurement evolves. This is what cosmologists mean when they say space expands. It's like the rules of measurement themselves shift. Once you adopt that idea, the question what is it expanding into becomes less meaningful because the growth isn't movement through a larger area. It's a change in the structure of the area we're talking about. Another useful angle is to look at how we define the universe. In science, the universe isn't a thing located somewhere. It's the sum of all physical existence, matter, energy, space, and time. If there were an outside, it would automatically become part of the universe. So by definition, the universe can't expand into something that isn't included. That might sound like a word game, but it reflects a deeper point. The universe is not a localized object. It's the framework that everything exists within. Asking what it expands into is like asking what the shape of all shapes is embedded in. The question only makes sense if you assume an external backdrop, and modern physics tells us there isn't one. Still, people tend to look for a picture they can visualize, and here's where a lot of explanations unintentionally create more confusion than clarity. When you hear that the universe might be curved, or finite but unbounded, or similar to the surface of a sphere but in higher dimensions, it's easy to latch onto the image of a sphere sitting in a larger room. But the spherical surface comparison doesn't refer to a physical object floating somewhere. It refers to a type of geometry that doesn't require an outside. The surface of a sphere can be described entirely from within its own properties without referencing any surrounding space. That's why cosmologists use analogies like it. Unfortunately, those analogies accidentally encourage people to imagine an external space anyway. because we're so used to picturing spheres from the outside. This is why the question at the heart of this video is so compelling. It exposes the point where everyday thought stops working, and physics forces us to think differently. It's not that the universe is weird just to be weird, it's that the rules we grew up with are based on small-scale environments, and the cosmos operates on scales where different rules take over. But there's something comforting in this shift. When you untangle the intuition, the actual picture becomes cleaner. Instead of imagining a giant bubble expanding into an infinite void, you imagine a network of distances changing within a system that contains everything that exists. Nothing outside hidden. Nothing beyond waiting to be discovered. Just space-time responding to the energy and matter inside it. When people use the word universe in everyday conversation, they usually mean something simple. The big thing out there that holds all the galaxies. It sounds straightforward, but in modern cosmology, that single word carries layers of meaning, and mixing them up is one of the fastest ways to get confused about expansion, boundaries, or the outside. Before going deeper into how space behaves, it helps to pin down exactly what scientists mean when they say universe, because the definition shapes every part of the discussion. The biggest issue is that we often use the same word for three different concepts: the observable universe, the entire physical universe, and the universe as space-time. These aren't different regions, they're different ways of framing what we're talking about. If they blur together, questions like expand into what become almost impossible to sort out. The version most people are familiar with is the observable universe, the region we can see from Earth simply because light has had time to reach us since the Big Bang. This region has a radius of about 46 billion light-years in every direction. It's not 13.8 billion because expansion has stretched space while the light was traveling. But the key point is that this boundary isn't a physical edge. It's not a wall, a membrane, or a border that marks the end of existence. It's just the limit set by the speed of light and the age of the cosmos. If you lived on a distant galaxy, your observable universe would be a different sphere because you'd be centered in a different place. Every location has its own observable universe. That alone tells you that this boundary is more about perspective than structure. This distinction matters because a lot of people hear observable universe and think the universe. Then they picture that sphere expanding, which instantly encourages the idea that the sphere must be growing into some larger space. But the observable universe is not the whole thing. It's the part we're able to receive information from. The actual universe, meaning everything that exists, could be vastly larger. It might even be infinite, and even if it's finite, it doesn't have to have an outer surface. It's entirely possible to have something finite that loops back on itself with no edge at all. The important part here is that the observable universe grows as time passes because we receive light from farther and farther distances. That's not expansion into anything, it's simply light arriving from regions that were previously too distant in look-back time. The second meaning of universe is the entire physical universe, the complete set of everything that exists, regardless of what we can see. This is closer to what cosmologists mean when they talk about the large-scale structure of reality. When they run simulations, write equations, or describe expansion, this is usually the universe they're referring to. And in this sense, the universe isn't a thing sitting in a larger container. It's the totality of matter, energy, and the fabric that holds them. Anything that could count as outside would, by definition, become part of the universe because it would exist. That sounds almost philosophical, but it's not. It's a direct consequence of using universe to describe the set of everything physical. If something exists, it belongs to the universe. If something is truly outside, meaning it doesn't interact, doesn't exist physically, isn't part of space-time, and has no definable location, then calling it an outside stops being meaningful. For cosmologists, the universe in this second sense is not a bubble that floats somewhere. It doesn't occupy a location. The reason this is hard to visualize is because our brains insist on giving everything a setting. Every object we've ever seen has been located somewhere. Everything we've ever touched exists in a room, on a surface, in an environment. So when someone describes something as a set of everything, it's incredibly tempting to imagine it as a huge object inside a bigger, emptier background. But the whole point of this definition is that there is no background. There is no place where the universe is. The universe is the place. Asking where it sits is like asking where space is stored. The third meaning is the most abstract, but also the most important: the universe as space-time. This is how general relativity frames the cosmos. In physics, space and time aren't just settings. They're dynamic, geometric ingredients. They can stretch, curve, ripple, and evolve. They respond to mass and energy, and that response tells objects how to move. When cosmologists talk about expansion, they're referring to changes in the geometry of space-time itself, not to galaxies drifting into a larger void. Distances increase because the metric, the mathematical rule that tells you how far apart points are, changes as the universe evolves. This is also the meaning that makes the question, what is it expanding into, lose its footing. Expansion isn't motion through a surrounding emptiness. It's a transformation of the distances within the space-time fabric. To get comfortable with this idea, it helps to think about how we describe space independent of any external reference. You don't need a higher dimensional environment to talk about the geometry of the surface of a sphere. You can describe latitude, longitude, distances, and curvature using only rules that apply within the surface itself. You don't have to imagine the sphere sitting in a bigger space to build a complete description. In the same way, cosmologists can describe three-dimensional space with whatever curvature it may have purely from within. The outside isn't a necessary part of the model. This internal description is all you need to define expansion, curvature, or the overall evolution of the universe. A major complication arises because people often mix these three meanings together without realizing it. Someone will hear that the observable universe is 46 billion light-years in radius, and they'll picture that sphere as the whole universe. Then they hear that the universe is expanding and imagine that specific sphere growing. Then they hear that space is expanding and think of the sphere pushing outward into a larger void. But cosmology does not combine these ideas that way. The observable universe is a growing horizon, not a structure. The physical universe is the total existence, not an object. And space-time is the framework that expands, not something that moves within a bigger arena. Once you keep these meanings separate, a lot of confusing questions dissolve. For example, people sometimes ask whether the universe has a center. If they're referring to the observable universe, then yes, you're at the center of your observable sphere. But so is every observer everywhere else. If they're referring to the physical universe, then no, there isn't a privileged center because expansion occurs uniformly. And if they're referring to space-time itself, the concept of a center doesn't even apply because the geometry doesn't single out a location where expansion begins. Expansion stretches the entire arrangement of distances evenly. Another example is the question of edges. The observable universe has a visible limit, but no physical edge. The physical universe might have no boundary at all, or it might be finite and unbounded, like the surface of a sphere. And space-time, as described by general relativity, doesn't require any kind of boundary in order to expand. None of these edges corresponds to an actual border that the universe could push against. They're conceptual boundaries that arise from how we define what we can see or how we model the geometry. Understanding the word universe also helps clarify the role of the Big Bang. Many people imagine the Big Bang as an explosion that happened at a point and expanded outward into emptiness. That's because they're adopting the everyday meaning, a physical thing surrounded by a bigger container. But in the space-time sense, the Big Bang wasn't an explosion inside space. It was an event in which space itself reached extremely high density and temperature everywhere at once. There was no outside for it to expand into. There wasn't even a pre-existing place where the event occurred. The universe didn't appear somewhere. It just existed from its earliest moment and kept evolving. Once you're thinking in terms of space-time, expansion becomes straightforward, and the distances between galaxies grow because the geometry changes. Galaxies move apart not because they're traveling through space into new territory, but because the metric that defines distance stretches. At small scales, local forces like gravity and electromagnetism overpower this stretching, which is why galaxies, solar systems, and atoms don't expand. Expansion only shows up over enormous distances where no structure holds things tightly together, and that kind of expansion doesn't need an external void. It only requires that space-time itself follow the equations laid out by general relativity. There's another important shift that comes from understanding the universe as space-time. Time is part of the system, not an external clock. When cosmologists describe the universe evolving, they're describing the way space-time changes from one moment to the next within its own framework. They're not watching it from the outside. There is no outside time ticking along. The timeline of the universe is internal. That's why questions like what happened before the Big Bang are tricky. The usual meaning of before breaks down when you're talking about the earliest definable moment of time itself. And that reinforces the larger point. The universe isn't an object moving through a bigger environment. It's the environment. A useful analogy, not perfect but helpful, is to think of a map rather than a landscape. If you imagine a map that slowly stretches so that the distances between cities grow, you don't think of the map expanding into a bigger desk. The map itself changes scale. The relationship between the points is what changes. In cosmology, the map is space-time and the cities are galaxies. The idea of expansion refers to the change in those relationships, not to motion into a background. This analogy isn't exact. Space isn't a sheet of paper, but it captures the difference between stretching a structure and pushing an object outward. Once you adopt this view, the idea of an external space becomes unnecessary. It's not that there's something beyond the universe that we haven't found. It's that the very notion of beyond doesn't connect to anything physical. If there was something physically meaningful outside space-time, it would require its own laws, its own geometry, its own notion of distance and interaction. As soon as any part of that became measurable or influential, it would become part of the universe by definition. If it never interacts and never has physical meaning, calling it an outside is equivalent to saying nothing. It's not a place where expansion could occur. The three-layer understanding of the universe, observable, physical, and space-time, also helps with another subtle issue. The universe doesn't expand at a single rate everywhere. The expansion rate we refer to, the Hubble parameter, is something that applies to large-scale distances between unbound structures. It's not a universal speed of expansion. And because the expansion affects the metric and not motion through space, it doesn't violate limits like the speed of light. Two distant galaxies can separate faster than light because nothing is traveling through space that fast. Space itself is changing. This is another case where the space-time definition avoids confusion that would come from treating the universe as an object flying apart. At this point, the idea of the universe as space-time might feel abstract, but that's because it is, and because nothing in everyday experience works this way. But as soon as you use this definition, everything else snaps into place. Expansion doesn't require an outside. The Big Bang wasn't an explosion. The universe doesn't sit anywhere. It doesn't have a center, and it doesn't need a boundary to avoid spilling into something else. The entire framework becomes self-contained. This is why cosmologists are careful with terminology. Words like radius, size, growth, and edge can be misleading unless you specify which meaning of universe you're using. The observable universe has a radius. The physical universe might have a size or might not, depending on whether it's finite. And space-time doesn't expand by growing outward. It expands by altering its internal geometry. For most of human history, people assumed the universe was eternal, fixed, and unmoving. Stars circled overhead, seasons changed, and planets wandered, but the large-scale structure of the cosmos seemed constant. Even when telescopes became powerful enough to reveal thousands of fuzzy objects scattered across the sky, the assumption didn't change much. Those smudges were simply thought to be clouds or star clusters inside our own Milky Way. Nothing suggested that the universe itself could be dynamic. In fact, even many early 20th century physicists favored a universe that simply sat there, unchanged, stretching infinitely in all directions, or looping back on itself in some stable balance. The idea of expansion didn't just seem unlikely, it wasn't even a serious option for most scientists. The first crack in that picture came from a surprising corner: subtle features hidden in the light from distant nebulae. Astronomers had begun using spectrographs to examine the light from these faint spiral patches, breaking the light into its component wavelengths. The goal was to understand their composition, their temperature, and possibly their motion. What they found instead was a consistent shift in the light from many of these objects toward the red end of the spectrum. At first, this wasn't interpreted as anything cosmic. A shift in wavelength often meant an object was moving relative to Earth. But the scale of the shifts turned out to be huge, far larger than anything astronomers expected from objects inside the Milky Way. It suggested either the measurements were wrong or these nebulae were traveling at astonishing speeds. The next major leap came from a simple but extremely powerful insight about certain stars. Henrietta Swan Leavitt, studying variable stars known as Cepheids, noticed a precise relationship between how fast they brightened and dimmed and how luminous they actually were. Faster pulsing Cepheids were dimmer, slower ones were brighter. That means you can measure how bright a Cepheid appears from Earth, measure its pulse rate, and from that you can calculate exactly how far away it must be. This became one of the most important standard candles in astronomy because it allowed astronomers to measure distances across deep space for the first time with confidence. Edwin Hubble took Leavitt's discovery and applied it to spiral nebulae. In 1923, he identified Cepheid variable stars in what was then thought to be the Andromeda Nebula. Using the pulsation-brightness relationship, he calculated Andromeda's distance, and the result was shocking. It wasn't simply far away, it was way beyond the outer edges of the Milky Way. This meant Andromeda was not a cloud inside our galaxy. It was a galaxy of its own, comparable in size to the Milky Way, separated from us by millions of light-years of empty space. Suddenly, the universe had grown far larger than anyone had imagined. Astronomers had no choice but to accept that the Milky Way was just one island of stars in a sea full of others. Once the idea of galaxies became established, the question of their motion returned to the forefront. Those redshifts observed earlier needed a better explanation. If these galaxies were truly outside the Milky Way, then their speed relative to us was part of a much bigger story. With the discovery that the universe contained countless galaxies, astronomers now had the opportunity to track these redshifts in a structured way. The next phase involved gathering precise distances to as many galaxies as possible and comparing those distances with their redshift measurements. By 1929, Hubble had compiled a substantial set of data with the help of other astronomers who carried out difficult, time-consuming observations from mountaintop observatories. When he plotted the distances of galaxies against their redshifts, the pattern was unmistakable. The farther away a galaxy was, the more its light was shifted to the red, and the faster it seemed to be moving away. The trend wasn't weak or fuzzy, it was a clean, rising line. That relationship is now known as Hubble's law. The recessional velocity of a galaxy is proportional to its distance. In simple terms, distant galaxies aren't just moving away from us, they're moving away faster the farther they are. This result caught the scientific world off guard. It suggested something far more dramatic than galaxies drifting randomly through space. If every distant galaxy showed the same trend, the simplest interpretation was that space itself was expanding. All galaxies weren't racing away because they were each given some powerful initial shove. Instead, the fabric of space that separated them was stretching. As space expanded, the galaxies that were farther from us experienced more stretch, and therefore their light was redshifted more strongly. That was why distant galaxies appeared to recede faster. It wasn't their individual motion, it was the effect of space growing between us and them. This idea might seem straightforward now, but at the time it was revolutionary. Even Einstein had originally introduced a cosmological constant to force his equations into predicting a static universe because he found the idea of expansion unsettling. When he realized that his own equations naturally predicted a dynamic universe without the extra constant, he reportedly called the constant his greatest blunder. Whether or not he actually used those exact words, the point stands. The evidence for expansion changed the entire direction of cosmology. As the discovery spread, scientists found themselves rethinking earlier assumptions. If the universe was expanding today, it must have been smaller in the past. Not smaller in the sense of being inside something, but smaller in the sense that distances between galaxies were less. That realization quickly led to a deeper idea. If you run the clock backward, the universe becomes denser, hotter, and more compressed. At some finite time in the past, later calculated to be around 13.8 billion years ago, the universe would reach a state where the density was extremely high. That idea became the foundation for the Big Bang model. But even before the Big Bang concept took shape, astronomers had to grapple with a subtle distinction. The galaxies weren't flying through a pre-existing empty background. The expansion was something that happened to the structure of space-time itself. This crucial detail caused confusion and debate because the way Hubble's results were often phrased, galaxies moving away at speeds proportional to distance, made it sound like regular motion. But regular motion alone can't explain why every distant galaxy recedes from every other in the same way, no matter which galaxy you choose as your reference point. If the expansion was simply motion, there would have to be a central point where all the galaxies originally flew apart, but observations immediately ruled out any center. No matter where you stand in the universe, the expansion looks the same. That's only possible if space expands uniformly. Another important development came from improvements in technology. Telescopes became larger, detectors became more sensitive, and the tools used to study spectra grew more precise. Astronomers could now analyze fainter galaxies and detect redshifts at scales much greater than Hubble's original set. Over the decades, thousands of galaxies were measured, and the pattern of expansion held up consistently. No part of the sky contradicted the trend. The expansion was real and it was universal. The story didn't stop there. As measurements improved, scientists noticed that the rate of expansion wasn't constant. It wasn't slowing down as much as expected from the gravitational pull of all the matter in the universe. In fact, by the late 1990s, multiple independent teams found evidence that the expansion was accelerating. This revealed that something, eventually named dark energy, was influencing the expansion. But even that discovery built on the work of Hubble, Slipher, Leavitt, and the early astronomers who first connected distance, motion, and cosmic scale. The early history of discovering expansion also includes an important shift in mindset. Before the 1920s, most scientists thought of the universe as static because that felt intuitively right. Motion requires forces. Forces need causes. If stars and galaxies weren't flying apart wildly, why would the entire universe be changing? The idea of a dynamic universe was not just unfamiliar, it seemed unnecessary. Hubble's discovery forced everyone to reconsider. Instead of relying on intuition, cosmology began relying heavily on measurable, quantifiable evidence. And that evidence consistently pointed toward an evolving universe. Another subtle but important part of this history is that the concept of expansion didn't immediately answer the deeper question: what is the universe expanding into? Many people at the time assumed the expansion must involve motion through some larger space. The idea that space itself expands wasn't obvious from the raw data. It was the interpretation that best matched all the observations and the mathematics of general relativity. It took years for the scientific community to fully internalize that expansion meant changing distances, not movement into an external void. The observational approach strengthened over time. Astronomers built a cosmic distance ladder, combining different methods: Cepheids, red giant stars, type Ia supernova, surface brightness fluctuations, and other techniques to calibrate distances more precisely across different scales. As each rung of the ladder improved, the measurements of expansion grew more refined. You can think of this as checking the same relationship from multiple angles. If every independent method agrees, the underlying picture is almost certainly correct. That's exactly what happened. Every approach confirmed that space expands. One of the striking features of this discovery is that the expansion doesn't look like an explosion. Explosions throw material outward into a surrounding environment. If the universe were doing that, galaxies would show a pattern of motion radiating from a single central point. But no such pattern exists. Instead, any observer anywhere in the universe would see the same trend: every distant galaxy moving away and more distant galaxies retreating faster. That's only possible if expansion is not motion through a background but a feature of space-time itself. Through the 20th century, as more data accumulated, cosmologists refined the equations that describe cosmic expansion. These equations, originally derived from general relativity, match the observed behavior of galaxies far better than any model involving simple outward motion. They predict how the expansion rate changes over billions of years, how the early universe behaved, and how large-scale structures formed. And all of that consistency points back to Hubble's original discovery: a straight-line relationship between distance and redshift. Today, the historical path to discovering expansion is seen as one of the turning points in science. It transformed cosmology from a philosophical field into one grounded in measurement. It revealed that the universe evolves. It laid the foundation for understanding cosmic history, from the Big Bang to the acceleration we see today. And most importantly for this video, It provided the evidence that forced scientists to ask new questions, not just how fast the universe expands, but what expansion actually is. This chapter matters because it shows that expansion wasn't an idea created to answer a theoretical puzzle. It was a direct takeaway from data. And the moment astronomers accepted that galaxies weren't drifting randomly but were carried apart by expanding space, the familiar question arose almost immediately. If space expands, what exactly is it expanding into? When people hear that the universe is expanding, the most natural picture is a cluster of galaxies flying outward into emptiness like shrapnel from an explosion. That is the image our brains default to because it matches how motion works in daily life. But what cosmologists mean by expansion is very different. It's not motion through a larger background. It's a change in the geometry of space-time itself, the underlying structure that tells everything how to move. Understanding this shift in perspective is one of the most important steps in understanding why the universe doesn't need an outside to expand into. To get there, it helps to start with what space-time actually is. In general relativity, space and time aren't passive arenas where objects move. They're dynamic. Mass and energy tell space-time how to curve, and the curvature tells objects how to travel. That means distances, angles, and even the rate at which time passes can vary depending on what the universe contains. Space-time is flexible rather than rigid. When cosmologists describe the large-scale behavior of the universe, they're describing how this flexible geometry evolves over time. One of the big consequences of this idea is that distance in cosmology is not the same as distance in everyday life. In ordinary situations, if you want to measure how far apart two objects are, you stretch a ruler or a tape measure between them. In the universe, that ruler is built into the geometry itself. The metric, which is a mathematical recipe for calculating distance, can change as the universe evolves. This is what expansion actually means. The metric stretches. 2 points that once had a certain distance between them can end up farther apart later, even if neither point has moved through space. The change comes from the fabric of space itself. A good way to visualize this, without falling into the trap of imagining an outside, is to think about a map rather than a balloon or a cloud of debris. Imagine a map printed on a rubber sheet. If you gently stretch the sheet, the distances between cities increase. The cities don't move across the sheet because of engines or winds. Their separation increases because the surface beneath them has stretched. You don't need a larger table underneath the sheet to understand the change. The map itself holds all the information. Now, this analogy isn't perfect because it uses a two-dimensional surface embedded in a room, and the universe isn't literally sitting in a room. But the key idea carries over. Expansion can be about the relationships between points changing, not about motion into somewhere else. In the real universe, the points are galaxies that are far enough apart that nothing holds them tightly together. At smaller scales, space doesn't stretch noticeably because stronger forces dominate. Gravity keeps your local group of galaxies bound. Gravity and electromagnetic forces keep solar systems, planets, and atoms together. Expansion only becomes visible over enormous distances where no internal forces counter it. That's why galaxies don't swell and stars don't drift apart internally when the universe expands. The stretching of space-time is incredibly gentle on small scales, and the local forces easily overpower it. But across millions or billions of light years, the accumulated effect becomes significant. This is the heart of why expanding space-time looks like galaxies receding. Their distances grow because the underlying metric grows. And from Earth, we detect this through the light they send us. Light waves traveling across expanding space get stretched too, which is why distant galaxies appear redshifted. Their light has longer wavelengths by the time it reaches us because the space it traveled through expanded. This idea was one of the big clues that expansion wasn't just motion. Light from galaxies doesn't show the kind of Doppler shift you'd expect from simple movement through static space. Instead, the wavelengths scale with the expansion factor of the universe itself. The redshift becomes a measure of the accumulated stretching of space, rather than a measure of the galaxy's individual speeds. Another important point is that expansion doesn't single out any location as the center. If galaxies were flying apart from a central explosion, there would be one privileged point where the blast happened. Observers near that spot would see galaxies moving mainly outward, while observers far away would see a skewed pattern. That is not what astronomers observe. Everywhere we look, the expansion appears uniform. No matter which direction you point a telescope, the large-scale redshift pattern is the same. The only way this can happen is if expansion occurs everywhere, not outward from somewhere. And the only framework that naturally produces that behavior is the stretching of space-time itself. When space-time expands uniformly, every point becomes a kind of center in the sense that every observer sees other distant galaxies receding. The mathematics behind this idea is surprisingly elegant. Instead of describing each galaxy's motion individually, cosmologists describe how the scale of the entire universe changes over time. That scale factor, usually represented by a TB, tells you how large the universe is at any given moment compared to some reference time. When a T increases, the universe expands. When it decreases, the universe contracts. The key is that this scale factor multiplies distances. It doesn't push galaxies outward. It stretches the coordinate grid itself. You can think of the grid as the invisible scaffolding that tells you how far apart things are. Expansion means the spacing of the grid grows. This might sound abstract, but it explains several features of the universe that would be strange if expansion were just motion. For example, many galaxies we observe are receding faster than the speed of light. That sounds impossible at first because nothing can move through space faster than light. But nothing in these cases is moving through space at that speed. The space between us and those galaxies is expanding. Light speed limits apply to motion within space-time, not to the rate at which space-time itself can stretch. When people hear that phrase, faster than light, it's easy to think of it as an error or contradiction. But once you treat expansion as metric stretching, it becomes completely normal. Another thing expansion explains is why the universe looks roughly the same in every direction at large scales, even though distant regions have never interacted. When you see uniformity across regions that were far apart from the very beginning, you need a mechanism that sets up that uniformity early on. Early cosmic inflation, a brief period of extremely rapid expansion, explains this by stretching small, smooth regions to enormous sizes. But that inflationary stage only makes sense if space-time itself can stretch. Motion through a larger static backdrop wouldn't produce the same result. Treating expansion as metric stretching also clarifies why there is no meaningful way to ask what the universe expands into. If distance is part of the internal geometry and the geometry itself evolves, then the outside concept doesn't apply. It's like asking what the changing temperature of the atmosphere is expanding into. Temperature doesn't expand into anything. It changes conditions within a system. The scale factor in cosmology works the same way. It changes the relationships between points inside space-time. Sometimes people ask if expansion means new space is being created. The word created is tricky because it implies some external supply or reservoir. But expansion doesn't require anything external. It simply means the metric evolves and the volume it defines increases. No matter creation required. No emptiness waiting. No background container. Just space-time changing according to its own dynamics. This is another place where everyday intuition makes things harder. When you inflate a balloon, you pump in air, and the space inside grows. When you knead dough, gas bubbles expand because yeast produces more gas. Every example we're familiar with involves adding something or pushing against something, but space-time is not a substance, and expansion is not driven by pressure from inside or from a boundary. It's a geometric change. This becomes easier to internalize when you think about curvature. In general relativity, curvature tells you how space bends. It doesn't tell you how space bends into anything. You can have curvature without embedding the object in a higher dimensional arena. Mathematicians call this intrinsic curvature. Take the surface of a sphere. You can describe its curvature entirely by measuring distances and angles within the surface. You never need to reference the space outside the sphere. The surface's geometry is complete on its own. In the same way, the geometry of our universe, and including its expansion, is complete without needing an external environment. Another angle that helps is imagining time as part of the same system. Expansion isn't a spatial change happening in time, as if time were externally imposed. Time is internal to space-time. Expansion is an evolution of the entire structure, not a motion through a stage. That means asking what happened before expansion began is also delicate, because before may not apply if time itself doesn't extend past a certain point. This isn't meant to be mysterious, it's simply what the equations say. If time has a starting point the way a line segment has an endpoint, then asking what came before is like asking what's north of the North Pole. The question uses concepts that don't apply outside the domain they're defined in. A question people also wrestle with is whether expansion changes the speed at which we move. If space-time stretches, does everything drift apart inside it? The answer is that local physics remains the same. Expansion only shows up when gravitational or electromagnetic binding is too weak to counter it. So your room doesn't grow, the Earth doesn't drift from the Sun, the Milky Way doesn't balloon. These systems are decoupled from expansion because they're held together by forces that overpower the gentle stretching of space. To see expansion, you need to look far beyond these bound systems to distances where galaxies aren't gravitationally connected. This detail also ties back to why the universe doesn't expand like an explosion. In a real explosion, the expanding material slows down over time as it transfers energy into the surrounding environment. With metric expansion, there's no friction and no surrounding environment. Space doesn't expand because it's pushing into something. It expands because the equations that govern its evolution give that result based on the energy content of the universe. As matter, radiation, and dark energy change over the lifetime of the cosmos, the expansion rate changes with them. Once you begin to see expansion as the stretching of space-time, the entire topic becomes cleaner. The strange paradoxes evaporate. You don't need a center, you don't need an edge, you don't need an outside. Expansion becomes a property of the universe itself, rather than a motion through something else. And instead of thinking about the universe as a physical object, you begin to think of it as a system whose geometry has a history, just like its matter and energy. This shift also makes later parts of cosmology easier to understand. Ideas like dark energy, inflation, the cosmic microwave background, and even the far future of the universe all rely on this geometric interpretation of expansion. None of them make sense in a picture where galaxies explode outward into a pre-existing void. They only fit together coherently when space can stretch, and when stretching is understood as a change within space-time rather than movement through something external. That's the core of expansion. Distances grow because space-time evolves, not because the universe is carving out new territory in a larger environment. Not because something outside gives it room. Expansion is internal. It's geometric. And once you treat it that way, the big question, what is it expanding into, shifts from a puzzle to an insight about why the question doesn't actually describe what's happening. Understanding expansion as a stretching of space-time isn't just a theoretical convenience. It matches real observations, and those observations help us see why the expanding into something picture fails. When astronomers look deep into the cosmos, they see distant galaxies whose light is shifted toward the red end of the spectrum. That redshift is not the same as the Doppler shift associated with a car speeding away on a highway. Instead, it carries the signature of space being stretched while the light travels. The light waves get elongated because the metric, the rule for distance and time in space-time, expands, so by the time the light reaches us, its wavelengths are longer. The more stretching that happened, the greater the redshift. That matches what we observe. The farther away a galaxy is, the more redshifted its light appears. Parallel to that, we measure how far away those galaxies are using various rulers or cosmic yardsticks. Some of those yardsticks rely on star types whose intrinsic brightness we know well, so we can infer distance from how dim they appear. Others rely on characteristic patterns in galaxies or supernovae whose energy output follows known rules. When distance measures and redshift measures match in the way predicted by a stretching metric, it strongly supports the idea that space itself expands. Another observational clue: the expansion doesn't behave like a classical explosion. In an explosion, you'd expect debris to speed outward with faster velocities the closer objects are to the source, and for there to be a center and boundary. But what we observe in the universe is uniform expansion. Wherever you are and whichever distant galaxy you look at, you see the same trend. Galaxies receding, with more distant ones receding faster. There is no special center. There is no outer boundary we can see or reach. The expansion looks the same in every direction and from every vantage point. That symmetry matches exactly what you expect if space-time itself is expanding. Also, when we examine smaller systems, atoms, planets, stars, galaxies, galaxy clusters, they do not expand. Their sizes remain stable over billions of years. That's because local forces, gravity, electromagnetism, atomic forces, dominate on those scales. The stretching of space-time is extremely gentle and only becomes manifest across vast expanses where nothing else holds the structure together. That explains why we don't see our solar system or Earth slowly growing larger, even though space is expanding. Putting together all these strands, redshift of distant light, distance measurements, uniform recession from every viewpoint, bound systems remaining unchanged, gives a coherent picture. The universe's expansion is about the internal geometry of space-time evolving. There's no need for space outside the universe, no need for a container or a void into which everything moves. The expansion is a change in scale, the stretching of the metric, not motion through or into something. If you step back, it becomes clear that the idea of the universe expanding into an outside rests on a hidden assumption, that space is like a contained room or a container with walls, a place that holds everything and into which things can grow. That assumption seems natural because every expansion we see in daily life involves something growing inside a background. But when the object of expansion is space itself, that assumption collapses. Space-time is the background. There is nothing external to it. Once you accept that, the outer arena becomes unnecessary and conceptually meaningless. First, when we describe space-time in the framework of modern physics, we describe the geometry of relationships between points, distances, angles, curvature, not the embedding of those relationships in any larger backdrop. That geometry is wholly self-contained. You can specify every measurable property of the universe, how distances change, how light propagates, how gravity works, without ever referring to some larger space beyond. In physics terms, the universe is intrinsically defined. It doesn't need a higher dimensional space to exist or expand. Second, even the idea of outside space becomes problematic when you try to define it. If you imagined a bigger space beyond our universe, you'd need a way to link it physically to our own. A notion of distance, interaction, or geometry relative to our universe. That bigger space would need to obey its own rules, and you'd have to explain why we cannot detect it. If it doesn't interact or influence our universe, then calling it a space is just a semantic trick. It has no physical meaning. If it does interact, then it becomes part of the physical universe by definition. In other words, either that outside doesn't exist in any meaningful sense, or it's already part of the universe. There is no third option. Third, analogies that suggest a background, a balloon expanding into air, a drop spreading across a table, or a firework exploding into darkness, always bring along baggage from everyday experiences. They embed assumptions about boundaries, containers, and backgrounds that don't apply to space-time. Those analogies are useful for giving a rough sense of expansion, but they mislead once you try to extend them literally. Space doesn't inflate into pre-existing emptiness. Instead, the emptiness itself stretches. What used to be a certain distance becomes a greater distance, not because something moved into emptiness, but because emptiness redefined itself. Fourth, treating expansion as a change in internal geometry explains why cosmic expansion doesn't need a center. If expansion meant flying apart from a central point, we would expect to see that center as a preferred location. But observations show no such preferred point. Every observer sees the same pattern of expansion. That only happens if the expansion is built into the structure of space-time, not if it's motion away from a center inside a larger space. Space-time expanding uniformly means every point behaves the same, so every point is center in its own view. That symmetry only makes sense if there's no external arena. Fifth, thinking of the universe as confined to a container raises unsolvable questions. What's outside the container? Who made the container? What laws govern it? If you say a bigger space, then you have to ask whether that bigger space itself expands and whether it sits inside an even bigger space, and so on. That leads to an infinite regress. Physics gains nothing from inserting extra layers of space beyond what's observable or meaningful. The simplest models don't require those layers, and in science, when you have a self-consistent model that matches observations, simplicity tends to win. Lastly, from a practical standpoint, frames of reference matter. When we describe expansion, we use coordinates defined within space-time. We don't embed those coordinates in something else. The expansion is described by a scale factor that applies to internal coordinates. There's simply no exterior coordinate system in which the universe sits because nothing outside it exists to define those coordinates. The math works entirely inside. Trying to force an external coordinate system in would add unnecessary complexity without explanatory power, and that's a no-go in physics. Taken together, these points show why expansion doesn't need an external arena. The universe isn't expanding into space because space, as we know it, is the arena. When the arena itself changes, there is no outside required. The idea of outside into which everything expands arises only if you insist on treating space as if it were like a container. Once you shift perspective, the puzzle dissolves. When people hear that the observable universe has a radius, it sounds like a hint that the whole universe must have an edge. After all, if something has a radius, doesn't that imply a boundary? But what astronomers call the observable universe is not a physical bubble sitting inside a larger, all-encompassing structure. It's simply the region we can see, the region whose light has had enough time to reach us since the beginning of cosmic expansion. Understanding this distinction is essential because it's one of the biggest sources of confusion about what the universe actually is and what it means for it to expand. Start with the idea of a cosmic horizon. Light travels at a finite speed, and the universe has existed for a finite amount of time, so there are places far enough away that their light hasn't had the time to get here yet. Those regions exist, but they're invisible to us for now. The boundary between what we can see and what we can't is called the observable universe. That boundary isn't a physical edge, it's a limit imposed by time and light. Nothing special happens out there. Galaxies don't blink out or turn into something exotic once they cross that distance. They're just too far away for their signals to have reached us. Now add expansion to the picture. Because the universe expands while light travels, some galaxies that emitted light long ago were once closer, but are now much farther away. This makes the observable universe counterintuitive. Its radius isn't simply the age of the universe multiplied by the speed of light. It's larger because space stretched while the light was in transit. Right now, our observable universe has a radius of roughly 46 billion light-years, even though the universe is about 13.8 billion years old. That number surprises people because it feels like it should be impossible. How can we see something 46 billion light-years away in a 13.8 billion-year-old universe? The trick is understanding that space expanded while the light traveled, increasing the separation between us and the region where that light originated. The important part is that this radius describes our horizon. Another observer in a distant galaxy would have their own observable universe centered on them, containing regions we can't see at all. There is no universal bubble that encloses everything. Every vantage point carves out its own bubble of visibility. That pattern only makes sense if the observable universe boundary is not a wall, but a matter of how far light can travel. This also helps clarify why the observable universe changes over time. As the universe ages, light from more distant regions has time to reach us, so our horizon grows. However, because expansion also continues, and in our era accelerates, some regions recede so quickly that their light will never reach us, not even given infinite time. Those regions are not outside the universe. They're just beyond what we will ever be able to observe. The horizon is dynamic. It's a moving frontier, shaped partly by the age of the universe and partly by how fast expansion is proceeding. This idea becomes even clearer when you contrast the observable universe with the physical universe. When cosmologists use the term physical universe, they mean the entire space-time manifold, the full three-dimensional space at a given moment, along with its history through time. That entire manifold could be infinite, it might be finite. Current data lean in the direction of very nearly flat, which suggests that the universe could be infinite in extent. But because the observable portion is only a small region of whatever the total is, we can't determine the full size with complete certainty. The key point is that the physical universe is not defined by what we can see. It's defined by the geometry and the laws governing it. If the universe is infinite, then no observer can ever see it all, even given unlimited time. Horizons will always limit how much of the infinite structure is visible. If the universe is finite but unbounded, like the surface of a sphere extended into 3 dimensions, then traveling far enough in one direction could eventually bring you back to your starting point. That would mean space has a global shape without having edges. Finite and edgeless are not contradictions. They only sound contradictory because everyday experience has trained us to assume that something finite must have boundaries. But geometry doesn't require that. A two-dimensional surface can be finite without having an edge. A three-dimensional space can work the same way. From this perspective, the observable universe becomes more like the lit area of a room when your flashlight's beam is too weak to illuminate the far walls. The dark parts of the room don't disappear or stop existing. They're just out of reach, not part of your visible patch. And, crucially, your lit region grows as you upgrade your flashlight. In the cosmic analogy, as time passes and light has more opportunity to arrive. This distinction between observable and physical also plays a major role in thinking about cosmic expansion. When expanding space increases the distances between galaxies, it doesn't increase the size of the observable universe in the same way. Sometimes the observable region grows as new light reaches us. Sometimes expansion pulls distant regions away so rapidly that their light can't keep pace. This push and pull gives rise to multiple types of horizons: the particle horizon, the event horizon, the Hubble radius, each describing different limits on what can be seen or influenced. None of these horizons are physical walls. They're informational boundaries tied to how light and expansion compete. One of the most common misconceptions is the notion that because the observable universe has a radius, the universe itself must have expanded from a point roughly 13.8 billion years ago into what is now a sphere of a certain size. That picture is misleading in several ways. It suggests a center where the Big Bang happened, an outer edge that has been growing for billions of years, and an external void that the universe expands into. But the Big Bang wasn't an explosion of matter into empty space. It was the simultaneous beginning of space everywhere. The observable universe is not the remnant of a small, early ball of material blown outward. It's the part of the entire universe that has been able to send us light since the beginning. Another intuitive mistake is to imagine that the observable universe marks the boundary of reality. But the fact that we can't see beyond a certain distance says nothing about what lies beyond. The physical universe could extend indefinitely, and because expansion accelerates due to dark energy, many regions we see today will eventually cross a threshold where their light will no longer reach us. In the distant future, our observable universe will effectively shrink in terms of what we can interact with, even though the physical universe itself doesn't shrink. Expansion pulls parts of the universe out of our causal sphere, not out of existence. Sometimes people wonder if the observable universe being finite means the universe must have a shape like a sphere. But that shape belongs only to the observable region. The total universe may have a completely different global geometry. For example, the universe could be flat and infinite, like an endless plane, while the observable part is simply the patch we can access. Or the universe could be finite and curved, like a three-dimensional analog of a sphere, while the observable region is much smaller than the whole. There is no requirement that the observable region reflects the true shape or size of the full universe. This distinction also clarifies why questions like what is outside the universe, or what is beyond the boundary, arise in the first place. These questions blend the observable universe with the physical universe. When someone imagines an edge, they're usually imagining the edge of visibility and treating it as the edge of existence. Once you separate the two, the puzzle evaporates. The edge is just a light travel limit. It's not a cosmic wall, because the observable universe depends on where you are. It emphasizes another idea. No observer sees all of reality. Every galaxy has its own horizon, its own region of light and information. Two distant civilizations might never be able to communicate because each lies beyond the other's event horizon, even though both inhabit the same universe. Expansion shapes these causal boundaries. Regions drift away from each other so fast that signals cannot bridge the gap. This isn't a matter of walls or edges, it's a matter of geometry and the speed of information. Another helpful perspective is to remember that the observable universe wasn't always the size it is now. Early in cosmic history, it was tiny. As time passed, more and more distant regions became visible. But this doesn't mean the physical universe expanded into those regions. They were always part of the universe. They were simply out of reach until their light arrived. Likewise, in the very distant future, regions we can see today will fade beyond visibility as expansion accelerates. Again, the physical universe doesn't shrink. Our accessible bubble does. This is why cosmologists separate what we can observe from what likely exists. Observations give us a window, but the window is only a patch of the whole. The window also shifts and changes over time because of expansion. When you grasp this, the phrase universe expanding into nothing becomes unnecessary. The observable universe expands in the sense that we see more of reality as time goes on, at least until acceleration reverses that trend. But the physical universe doesn't expand into anything external. It expands internally as the metric evolves. In simple terms, the observable universe describes what we can see. The physical universe describes what exists. They are not the same thing, and confusing them leads to questions that seem profound but stem from mixing categories. Once you keep them separate, the structure of cosmology becomes clearer. Expansion reshapes what is visible, not where the universe is located. The universe doesn't sit inside a box, and the observable horizon isn't the box's edge. It's simply the distance light has been able to travel so far. If the entire universe is finite in size yet has no edge, meaning it's unbounded, that doesn't block expansion. In fact, many cosmological models allow exactly that. A universe that's finite in volume yet expands without ever growing into an outside. First, it helps to remember that finite doesn't always mean has a boundary. In mathematics and geometry, there are well-known shapes that are finite but unbounded. Think of a two-dimensional sphere, the surface of a ball. If you lived on that surface, you could walk in some direction forever and never hit an edge, because the surface loops back on itself. Still, the total surface area is finite. For a three-dimensional universe, the analogous shape is a three-sphere, or more generally, a closed three-manifold. In that scenario, space is finite. It has a finite volumes, but there is no boundary, no outside, no edge. If that kind of universe expands, expansion simply means the size scale of that three-sphere increases over time. Distances between points, or galaxies, grow because the geometry itself stretches. The universe doesn't expand into empty space. Instead, what changes is how the geometry measures separation. The shape expands from the inside. Even if the universe is infinite rather than closed, expansion still works. An infinite universe can stretch uniformly so that the distance between any two distant points increases. In that case, infinite remains infinite, but the spacing grows. It's a bit like taking an infinite grid drawn on a stretchy rubber sheet. You stretch the sheet, and the grid gets sparser. Distances increase. But there's never an edge, and the sheet is still infinite. What this shows is that expansion doesn't require a surrounding container. It doesn't require a boundary. It only requires that the geometry of space itself can scale. Whether space is finite or infinite, expanding is about changing internal distances, not about filling up new territory. Curved space is one of those ideas that sounds abstract until you connect it to something familiar. People often hear the phrase and picture space folding like paper or bending like metal. But curvature in physics isn't about bending into a higher dimension. It's about how distances and directions behave within the space itself. Once you understand that, it becomes much easier to see why the universe can expand without needing an outside, why straight lines can act strangely on cosmic scales, and why the overall shape of the universe matters even if there's nothing surrounding it. To get the idea across, start with something simple: drawing shapes on a flat surface. On flat paper, the rules of geometry behave the way you learned in school. Triangles have angles that add up to 180 degrees. Parallel lines never meet. The shortest path between 2 points is a straight line. Now imagine doing the same exercise on a globe. If you draw a triangle whose corners sit at the North Pole and 2 points on the equator, you can easily get a triangle with angles adding up to more than 180 degrees. If you draw parallel lines on a sphere, like 2 lines of longitude, they eventually meet at the poles. And if you try to find the shortest path between 2 points, that path curves on the surface even though it's still the straightest possible route in that geometry. None of those effects require the sphere to bend into any external space for them to be real. They're all intrinsic properties of the surface itself. The same internal logic applies to three-dimensional space. Space can be flat, positively curved, or negatively curved, and you don't need to imagine a higher dimension to make sense of it. In a positively curved universe, the 3D analog of a sphere, straight lines eventually loop back. If you traveled far enough in one direction, you could theoretically end up back where you started. In a negatively curved universe, like a 3D analog of a saddle, triangles have angles that add up to less than 180 degrees, and lines that start parallel tend to diverge. In a flat universe, the geometry follows the familiar rules of Euclid. What matters is that these differences show up in how distances and shapes behave, not in whether the universe sits inside something. This idea becomes even more important once you bring general relativity into the picture. Einstein's theory ties the curvature of spacetime to the amount and type of energy within it. Matter tells spacetime how to curve. Spacetime tells matter how to move. That means the geometry of the universe isn't fixed. It changes as the content of the universe changes. Early on, when the universe was dense, curvature behaved differently than it does today. As the universe expanded and matter thinned out, the geometry evolved. This dynamic relationship is one of the reasons expansion is possible at all. If the geometry can change, the scale of distances can change with it. Many people assume curvature must be visible in some dramatic way, like an optical illusion on the night sky. But curvature is subtle. If the universe is curved on scales far larger than the observable region, we simply wouldn't notice. Our local patch could look perfectly flat even if the global geometry is very different. It's like standing in a wheat field. From your perspective, the ground looks completely flat because the curvature of the Earth is far too gentle to detect without traveling far. In cosmology, we face the same limitation. We only observe a tiny portion of the whole universe. The curvature we measure applies to our observable patch. The full universe could be finite or infinite, positively or negatively curved, and we wouldn't know unless curvature leaves imprints in things like the cosmic microwave background. Despite these subtleties, curvature isn't a decorative detail. It affects how the universe expands. In a positively curved universe, too much matter could make expansion slow down enough to reverse, causing a collapse. In a negatively curved or flat but sparse universe, expansion continues indefinitely. Today's observations show that the universe is extremely close to flat. Not perfectly flat, it's almost impossible to tell, but close enough that flat models match what we see. That pushes cosmologists toward models where the universe might be infinite, or at least so large that curvature is too small for us to detect within our horizon. Curvature also clarifies why expansion doesn't mean things get stretched in ways we can feel. Since curvature describes geometric relationships, it's entirely possible for the universe's geometry to stretch while local systems remain unaffected. A curved space doesn't suddenly distort your room or stretch the distance between your hands. Local forces dominate at those scales. Curvature matters only when you look at the universe across billions of light years. On everyday scales, gravity and electromagnetism are thousands of trillions of times stronger than the gentle changes introduced by cosmic expansion. So even if curvature evolves, your kitchen table stays the same size. One of the hardest parts for people to internalize is how curvature connects to the no outside needed idea. When you think of curvature using the balloon analogy, it's natural to imagine the balloon surface needing a surrounding room. But the surface of the balloon doesn't need that room to define its geometry. The mathematics describing the surface is complete without referencing the air around it. The only reason we picture the balloon in a room is because we're visual creatures living in 3 spatial dimensions. In physics, the embedding space is purely optional. When talking about the universe, an embedding space is not only unnecessary, it leads to confusion. It tricks us into thinking expansion requires movement into something when the math says otherwise. Another surprisingly useful aspect of curvature is how it interacts with light. Light travels along the straightest possible paths in spacetime, called geodesics. In flat space, those paths look like straight lines. In curved space, they can bend or diverge. When astronomers survey the cosmic microwave background, the faint afterglow of the early universe, they look at tiny temperature patterns that stretch across the sky. Those patterns act like rulers. If the universe were strongly curved, those patterns would appear differently sized. Because the patterns match the expectations for almost flat geometry, curvature must be very mild. This doesn't mean the universe is definitely infinite, but it does mean the observable part doesn't show large curvature. Curvature also affects the question of how old the universe is. The relationship between expansion and curvature determines how quickly the universe grows with time. If curvature were strongly positive, expansion might have slowed and reversed early on. If strongly negative, expansion might have proceeded faster. The behavior we see today, expansion that slowed for billions of years, then began accelerating, fits a universe with very small curvature and a dominant contribution from dark energy. Again, this entire description depends on internal geometry, not external surroundings. Curved space can also help explain why the universe avoided an edge from the very beginning. If the universe started out with a closed geometry, like a small three-sphere, it could have expanded smoothly without ever having a boundary. Even if the inflationary period made the global geometry difficult to measure today, the idea that the universe never had edges fits naturally into curved space models. Edges would create special points, preferred directions, or discontinuities in the laws of physics. We see none of that in the data. Every direction in the sky behaves uniformly when averaged over large scales. That uniformity is exactly what you'd expect from a space without boundaries. Some people hear curved and imagine dramatic warping, but cosmic curvature has almost nothing to do with the kinds of bends you see in sci-fi movies where space twists visibly. Curvature at the scale of the universe is unbelievably gentle. It's so gentle that even across billions of light years, the effects are small enough to require precise measurements to detect. If the universe is curved, you wouldn't notice by looking at constellations. The night sky wouldn't appear distorted. Because the curvature radius, the scale at which geometry deviates significantly from flatness, could be far larger than our observable universe, everything we see might look perfectly normal, while the unseen whole could have a very different global shape. Curvature also gives a more intuitive way to understand why expanding space doesn't dilute everything evenly. Matter clumps under gravity. Radiation spreads. Dark energy, which acts like a uniform energy density, affects curvature differently than matter does. Each component influences the geometry in its own way. The tug-of-war between these components shapes the cosmic history. For example, during the early universe, radiation dominated and produced its own curvature behavior. Later, matter dominated and curvature effects shifted. Today, dark energy dominates, pushing curvature toward a state where expansion accelerates. These transitions show that curvature isn't a fixed backdrop. It evolves with the universe. Another way to think about curvature is by imagining what an observer could measure if they traveled long distances. In a positively curved universe, you could set off in one direction and eventually return from behind. In a negatively curved universe, you might find that the farther you travel, the more space seems to open up ahead of you, like walking across a surface that keeps expanding faster than you can traverse it. In a flat universe, none of that happens. These are not stories about entering new realms beyond the universe. They're stories about geometry shaping the paths and distances inside the universe. Everything is internal. Curvature also clarifies that expansion is not stretching a surface of nothing. It's altering the relationship between points. Even the idea that new space appears is just another way of saying the metric changed. Curvature and expansion are linked because they both describe how geometry evolves. If the universe were static and flat, those relationships would remain frozen. But our universe is dynamic. Distances grow. Curvature shifts. Expansion happens because the geometry is active, not because space pushes into a void. In the big picture, the reason curvature matters so much is that it gives us a language for understanding the universe that doesn't rely on comparisons to everyday objects. It lets us describe expansion, distance, motion, and gravity using internal rules instead of analogies. Once you understand curvature as an intrinsic property, the need for an outside disappears. There is no outside. There is only the geometry evolving with time. General relativity changes the entire discussion about expansion because it removes one of the oldest assumptions humans instinctively make about space: the idea that space is a passive container. Before Einstein, people pictured space as a stage on which events played out. The stage itself didn't do anything. It didn't bend, stretch, ripple, or interact. Objects moved within it, and space simply provided the backdrop. But once you adopt that picture, expansion automatically raises the expanding into what question. If space is a container and the container is getting bigger, then something must lie outside the container. When Einstein showed that space-time is not a container, but a dynamic physical entity, the old question became the wrong question. To see how this works, you have to start with the core idea. In general relativity, space-time tells matter how to move, and matter tells space-time how to curve. This isn't just a metaphor, it's a literal rule built into the equations. The geometry of space-time isn't optional. It has physical consequences. Curved space-time shapes the paths that objects follow, the way clocks tick, and the way light travels. When you combine that idea with a universe filled with matter, radiation, and dark energy, the geometry reacts. It changes over time. And that changing geometry is what we call expansion. This shift in perspective removes the idea that something needs to push from the outside or create additional room. Space behaves like a field. A field doesn't need an external environment to expand or change. It obeys its own internal equations. If a magnetic field grows stronger in one region and weaker in another, you don't ask what it's expanding into. You simply track how the field evolves. Space-time works the same way. Its structure evolves based on the distribution of energy and the rules encoded in Einstein's equations. No extra space is required, no container, no outer walls. A helpful way to think about this is to imagine that the distance between two objects isn't determined by a static grid. Instead, the grid itself is stretchy. If the grid stretches uniformly, distances increase. If the grid stays the same in a small region, local objects don't feel any change. That's how our universe behaves. The stretching of space-time happens on large scales, while local forces dominate in smaller systems. Gravity in a galaxy or the electromagnetic forces inside your body keep everything tightly bound. Expansion has almost no influence on those scales, but on the scale of millions or billions of light years, the stretch becomes noticeable. This may sound abstract, but it's part of the reason galaxies aren't flying apart while galaxy clusters gradually separate. The rules baked into general relativity allow different scales to behave differently. Space-time stretching is extremely gentle. Even between the Milky Way and the Andromeda galaxy, the pull of gravity outweighs expansion. That's why Andromeda is moving toward us rather than away. Expansion is not a wind or force that shoves galaxies around. It's the slow recalibration of the distances between unbound regions of space. Because the process is built into the geometry, there's no need to imagine new space being created in a place outside the universe. Another feature of general relativity that removes the need for an outside is its treatment of coordinates. In Newtonian thinking, coordinates describe positions inside a universal container. They refer to fixed background points. But in relativity, coordinates are just labels. They don't define anything physically unless you attach measurable meaning to them. That means you can't rely on everyday concepts like center, edge, or beyond, because those terms assume a stable backdrop. In relativity, the backdrop is the thing being described. Asking what lies beyond space-time is like asking what lies north of the North Pole. The question only makes sense if the underlying structure allows such a direction. Space-time does not. The famous example often used in classrooms is the balloon analogy, though it has limitations. If you draw galaxies on the surface of an inflating balloon, the galaxies move farther apart, even though the surface has no center and no edge. But in relativity, the balloon's third dimension isn't required. The surface has its own geometry. What you actually want to keep from that analogy is just one idea. Distances increase even though there is no direction pointing off the surface. The expansion is internal. General relativity allows that kind of behavior without any embedding space. The mathematics describes the evolution of the surface alone. One subtle but important point is that general relativity doesn't say space must expand. It says space will evolve depending on what fills it. If you had a universe with the right amount of matter and no dark energy, expansion could slow to a halt or even reverse. If you had a universe with much more dark energy, expansion would accelerate even faster than what we observe today. The geometry responds to what the universe contains. The fact that our universe is expanding and accelerating tells us something about the contents of the universe, not about anything outside it. Now someone might say, But if space-time controls distances, why can't that stretching happen by simply adding more space-time beyond the edges? The reason is that relativity does not define space-time as something that sits somewhere. Space-time is the structure of the somewhere. There is no physical meaning to adding more space outside because outside is not a location defined within the theory. For a location to exist, you'd need space-time there. If you speculate that there is an outer region with its own space-time, then that region becomes part of the universe. The universe isn't our visible portion, it's the entire connected space-time. Anything you add becomes part of the whole. So you can't meaningfully talk about the universe expanding into something else because the moment you name that something else, it's automatically included within the definition of the universe. General relativity also avoids the need for external space by describing expansion using the metric, a mathematical object that defines distances between nearby points. When the metric changes in time, distances change in time. There is no need for objects to move relative to an external reference frame. The only thing that changes is the relationship between points within the universe. In technical terms, expansion is a change in the scale factor, not a displacement into new territory. If the scale factor doubles, all unbound distances double. Nothing travels outward into pre-existing emptiness. Geometry simply redefines itself. Because distances depend on the metric, general relativity also predicts how light travels in an expanding universe. Light gets stretched. Its wavelength increases as space expands. This redshift is one of the most direct observational confirmations that expansion is real, but it also shows that expansion isn't a force that acts on objects. It acts on geometry. Astronomers observe galaxies whose light has been stretched by factors of 10 or more. That stretching happened because space-time itself expanded while the light was traveling. You don't need an outside to make that work. You just need changing geometry along the path of the photon. The elegance of general relativity is that it replaces older intuitive pictures with a precise, internally consistent framework. When galaxies recede from each other, it's not because they're flying through space into a vast empty region. It's because the metric evolves. When space expands, nothing pushes outward. When the universe grows, it does not grow into anything. The expansion is self-contained because the geometry is self-contained. This perspective also explains why the universe does not need a special location where expansion began. The Big Bang wasn't an explosion in space. It was the rapid evolution of space-time everywhere. Every point in today's universe corresponds to a point in the early universe. No spot was the center, and no region was the outside. General relativity makes this unavoidable. If you try to place the Big Bang at a point in some larger container, you're importing a picture that the theory does not use. Ultimately, general relativity eliminates the need for an outside because it gives the universe a set of internal rules that govern its shape, scale, and evolution. Nothing needs to exist beyond. Nothing needs to push in from the outside. Expansion is not an object moving, it's geometry changing. And because geometry is the framework rather than something sitting inside a framework, the question "what is it expanding into?" dissolves. Expansion happens within the universe because space-time is the universe. When cosmologists say there is nothing outside the universe, they're not talking about a dark, empty region surrounding it. They mean something much stronger and much less intuitive. The concept of an outside simply doesn't apply. There is no place where the universe sits, no external arena it occupies, and no external backdrop against which it moves or grows. This is one of the hardest ideas to internalize because everyday experience trains us to think spatially. Everything we know exists somewhere, and everything that grows expands into some surrounding environment. But the universe is not an object inside something larger. It's the entire collection of all physical locations, all space-time, all energy, all matter, the complete set of all places where physics operates. Once you grasp that definition, outside becomes impossible by definition, not just empty. This is easier to see when you separate two meanings of nothing. In everyday conversation, nothing often means empty space, a region where there's no matter, but space still exists. Cosmologists never use the word that way when discussing what lies beyond the universe, because that would imply the presence of a spatial region outside our own space-time. And if such a region existed and followed physical laws, then it would already be part of the universe. You cannot have empty space outside space-time because empty space itself is space-time. If there's space, there's geometry. If there's geometry, there's physics. And if there's physics, you're inside the universe. This is why nothing cannot mean empty space. It means no space. Another intuitive mistake is imagining the universe having a shape viewed from an external standpoint. People picture it like a bubble or a cloud or a glowing sphere suspended in a larger dimension. That's normal. Our minds like images. But any such picture sneaks in a hidden assumption that the universe has an outer surface, and outer surfaces only make sense if something sits in a background. A balloon has a skin because the balloon exists in a room, but the universe doesn't exist in a room. It doesn't float in a larger arena. Its geometry describes all possible locations. So asking what shape the universe has from the outside is like asking what the surface of Earth looks like from below the ground all the way at the bottom. The question assumes a viewpoint that cannot exist. A useful way to break that habit is to think about dimensions. Imagine a two-dimensional creature living on the surface of a sphere. That creature can move north, south, east, west, all directions that exist within the surface. But it cannot point up or down because those directions aren't part of its world. They're meaningless inside the geometry it lives in. For that creature, talking about the sphere needing an outside is as meaningless as someone asking what direction lies beyond the final direction on a compass. Humans experience 3 spatial dimensions, so we tend to imagine higher ones automatically. But nothing in physics requires them. The entire universe can have a complete 3D geometry without any extra direction for it to expand into. This doesn't mean the universe is finite or infinite. Both possibilities exist within general relativity. But whichever it is, the absence of an outside still holds. If the universe is infinite, there's simply no end to reach. There's no boundary to ask about. If it's finite but unbounded, like a 3D version of a sphere, then traveling forward forever wouldn't take you out of the universe. It would only bring you back around. A finite volume doesn't imply a surrounding exterior any more than the surface area of Earth implies an edge you can step off. The phrase "nothing outside the universe" also doesn't mean there is a barrier preventing exit. It means exit isn't a concept that applies. For an outside to exist, there must be a measurable distance to it. But distances require space-time. If space-time doesn't extend beyond the universe, and by definition it doesn't, then there's no distance to measure. Without distance, there is no location. And without location, directions like beyond, past, or outside lose meaning. They become grammatically correct but physically empty. The only places that exist are places within space-time. A good analogy is time. You can talk about what happened before you were born, but you can't ask what happened before time existed. Asking what lies outside the universe is similar. You're asking for a place outside the set of all places. Your language still works, the question is grammatically fine, but the concept collapses. It's like asking what color envy is. The grammar allows it, but the idea doesn't map to reality. This doesn't mean physicists avoid the question by definition. They avoid it because adding an outside violates the core definition of the universe as the totality of physical spacetime. If you introduce another region that exists outside, you've expanded the definition of the universe. You haven't created a meaningful outside. You've just enlarged the inside. The word universe is flexible. It expands to include any region that has structure, law, or physical effect. So every attempt to propose an outside either reduces to something unphysical, a direction that doesn't exist, or something that must be included by definition within the universe. You might wonder whether the universe could sit inside some larger structure we simply cannot detect. But if that larger structure obeys laws, has distances, and can in principle affect or be affected by our region, it is part of the universe. If it cannot interact in any way, then there is no physical sense in which it exists. In physics, existence requires interaction or measurability, even indirectly. A region that affects nothing and interacts with nothing is indistinguishable from a region that isn't there at all. That's why cosmologists don't talk about outside space unless they mean speculative models that redefine what universe refers to in the first place. The final piece of this idea is that expansion doesn't require anything beyond spacetime because expansion is a change in the geometry, not a movement through another place. When cosmologists say the universe expands, they're describing an internal process, distances within spacetime increasing over time. If you change the scale of those distances, you've expanded the universe without ever touching an outside. You change the metric, not the surroundings. When all of these pieces come together, the phrase "nothing outside the universe" becomes clearer. It means the universe isn't an object. It isn't a bubble. It isn't a speck within a void. It's the entire fabric of space and time, and everything that can take place happens within that fabric. Asking what lies beyond it is like asking what lies north of the North Pole. The question uses familiar words, but the underlying idea has no physical meaning. Multiverse theories have become so popular in science discussions that many people think they offer an easy answer to the expanding into what puzzle. It sounds simple. Maybe our universe is just one bubble among many, and it's expanding into a larger arena containing other bubbles. It feels like a neat solution because it preserves the familiar intuition that everything must sit inside something bigger. But when you dig into what physicists actually mean by a multiverse, you find that it doesn't rescue the idea of an external space at all. In fact, most multiverse models either leave the original question unchanged or make it even more subtle. They don't give the kind of outside people imagine, and they don't provide a container that our universe expands into. The word multiverse suggests layers, compartments, or different rooms in a mansion, but none of the serious models work that way. Start with the version people usually picture first. The idea that multiple universes float in some larger medium, like bubbles in a cosmic foam. This comes from a rough metaphor used in eternal inflation models. In those models, different regions of space-time stop inflating at different times, forming isolated pocket universes. It's tempting to imagine these pockets as bubbles expanding into a larger external space. But the picture is misleading because the larger space is still part of space-time. It's not an outside region in the everyday sense. The inflating background is itself space-time undergoing rapid expansion. When a bubble universe forms, it doesn't expand into a void that surrounds it. It expands because the geometry inside the bubble evolves differently from the geometry in the inflating region around it. There's no external room, no empty chamber, no absolute space that lies outside the entire structure. The bubble is part of the whole space-time fabric. If you insist on calling the inflating region an outside, then you've simply enlarged what you mean by universe. You haven't created something beyond the totality of space-time. Another common idea comes from string theory, where people talk about higher dimensional spaces, or branes, essentially membranes floating in a higher dimensional environment. Here too, it's easy to jump to the wrong conclusion. You might imagine our universe as a sheet suspended in some vast, higher dimensional expanse, and you might think that when our sheet expands, it spreads out within that higher dimensional space. But the physics doesn't require any such background to play a role in expansion. In brain models, the geometry on the brain evolves according to its own rules. The expansion we experience is internal to the brain. Even if the brain exists within a higher dimensional structure, the expansion of the brain does not rely on occupying more room in the higher dimensional environment. The metric that defines distances on the brain changes with time. That's the expansion. The higher dimensional space doesn't need to stretch, shrink, or serve as a container. It's just part of the theoretical framework, not a literal surrounding chamber. And again, if that higher dimensional structure exists and follows laws, it counts as part of the universe in the broad physical sense. You haven't found a real outside. You've only expanded the definition of inside. A different multiverse proposal arises from quantum mechanics, the many worlds interpretation. Here, the universe branches into different outcomes every time a quantum event with multiple possibilities occurs. People sometimes hear this and imagine parallel universes growing or splitting in a larger space, like pages being added to a book. But in many worlds, the branching is not a spatial separation. It's a separation in the configuration of the quantum state. These branches don't float next to each other. They don't drift apart. They don't occupy different regions of a surrounding void. They exist as different components of the universal wave function. Asking what lies between these universes is like asking what lies between two possible chess games that start from the same initial position. The question assumes a spatial connection that the theory doesn't actually describe. All of this shows that when scientists use the word multiverse, they're not proposing layers inside layers of containers. They're proposing different solutions to equations, different states of fields, or different regions of space-time that follow different physical rules. None of these automatically give you the external space that people imagine when they ask what the universe expands into. The structure in these models is internal. Even if a model includes a higher dimensional landscape, that landscape is part of the physical reality being described. In other words, it's part of the universe. Physicists use the word universe in two main ways, either as our observable region or as the entire physical structure that exists. In the second sense, the one used for these conceptual questions, any structure that can affect or be affected by anything else belongs to the universe. There is no outside left over. It's worth also looking at how inflationary multiverse models handle boundaries, because this is where misunderstandings multiply. In eternal inflation, the inflating background expands exponentially, while pockets where inflation ends become individual universes with their own internal expansion histories. It's natural to think, okay, so the pocket universe expands into the inflating background. But what's actually happening is that the pocket universe inherits a geometry that evolves according to the energy and fields inside it. The pocket grows because the space-time inside it continues to expand after inflation ends, not because it pushes into or occupies more of the inflating region. The inflating region itself expands even faster than the bubble. So instead of an expanding bubble carving out more room, you have a bubble whose boundary remains tiny compared to the rapidly growing environment. The bubble doesn't eat into the background. It just evolves according to its own internal geometry. If this all sounds strange, it's because the everyday idea of expansion breaks down when space-time itself is dynamic. You can't use balloon, soap bubble, or explosion imagery without distorting the actual physics. Even if you combine eternal inflation with string theory's landscape of possible vacuum states, you still don't get an external container. You get a patchwork of regions with different physical laws separated by inflating boundaries. But all of those regions are part of a single connected space-time structure. If you define universe as everything in that space-time, then the multiverse is just a larger universe. There's no surrounding medium. If you define universe as our low-energy region, then you've chosen a narrow definition. But the bigger space-time remains the totality. Once again, you don't get an outside. There's another twist. Even in multiverse models, the global structure may be infinite. And if it's infinite, there is no edge to expand into. Each region evolves internally. Expansion happens within each pocket. The inflating background also expands. But none of these changes require a location beyond the total physical space. It's just layers of internal geometry evolving under different conditions. You might get regions that grow, regions that collapse, regions that become empty, and regions that spawn new pockets. But the entire structure is still the whole of space-time. That means there is no external arena adding space around it. Everything is part of the same overall fabric. Another misconception is that multiverse ideas automatically imply something beyond the Big Bang, as if other universes existed first and ours sprouted inside them. But even in the models that try to address pre-Big Bang questions, such as bouncing cosmologies, loop quantum gravity scenarios, or certain string models, none of them introduce an external space. They propose conditions under which space-time transitions from one state to another. They don't put our universe inside something else. They change the state of space-time, not the container. You still have one continuous space-time, possibly with different phases, but never an outside region where the universe grows like a balloon. The irony is that multiverse theories, which many people believe give an external place, usually do the opposite. They reinforce the idea that what exists is everything connected through physical laws. If a region can interact with something else, then it's part of the universe defined in the broadest sense. If it cannot interact at all, then its existence becomes scientifically empty. You can imagine it, but nothing about it affects physics. From the standpoint of science, that's indistinguishable from nothing at all. So even if you picture countless isolated regions, the only ones that matter scientifically are those connected through the underlying laws, and those regions are all inside the same total structure. The key point is that multiverse ideas don't restore the everyday intuition that expansion requires a surrounding emptiness. They don't give you an arena around the universe. They don't give you a space beyond space-time. They complicate the internal structure of reality, but they don't create an external one. Expansion remains a property of the metric, the internal geometry, and not a movement into something. Whether space-time has one region or a million, expansion still happens within the space-time framework. The nothing outside the universe idea remains untouched. When you take a step back from all the speculative models, the bottom line becomes clear. Multiverse theories can give more regions, more histories, more possible physical laws, or more dimensions. But they never give a literal outside. The universe, in the broad physical sense, is still the totality of space-time. If a structure lies beyond space-time, it cannot be described with distances, directions, or physical interactions. And if it can't be described in those terms, it's not a place expansion could reach. Expansion is geometric evolution, not spatial travel. This is why cosmologists don't lean on multiverse ideas to answer what is the universe expanding into. They're interesting in their own right, but they don't solve that particular question. They leave the original conclusion intact. Expansion doesn't need an external realm. It happens entirely within space-time, and space-time is the whole of the physical arena. Inflation is one of the most counterintuitive but essential pieces of modern cosmology, and it plays directly into the question of expanding into what, because it shows the universe undergoing a phase of expansion so extreme that ordinary language becomes almost useless. Inflation refers to a brief period in the earliest fraction of a second after the Big Bang during which space didn't just expand. It expanded exponentially, doubling in size again and again at a staggering rate. But even here, even at this most dramatic moment, the expansion didn't happen into anything. It happened because the geometry of space-time was driven by energy conditions so intense that distances grew faster than any normal physical process could keep up with. The early universe didn't rush outward like an explosion into empty room. It rushed inward on itself, so to speak. Its own metrics stretched, leaving no need for an external arena. To understand why inflation was proposed in the first place, imagine trying to explain a universe that looks incredibly smooth and uniform in every direction. The cosmic microwave background, a leftover glow from the early universe, is almost the same temperature everywhere we look. But without inflation, there's a problem. The regions we see across the sky are so far apart that they never had time to interact or share information in the early universe. They should have grown independently and ended up with wildly different properties. Yet they didn't. They look coordinated. They look like they came from a single, well-mixed environment. Inflation solves this by saying the entire visible universe, and much more, came from a tiny patch of space-time that was already smooth, already uniform, and then that patch ballooned out at incredible speed. But the key is that it ballooned because space-time itself underwent a rapid, energy-driven stretching. Nothing sat outside waiting to receive it. Inflation also solves another old puzzle, the flatness problem. Observations show the universe is extremely close to geometrically flat. Not positively curved like a sphere, not negatively curved like a saddle. Without inflation, you'd need an almost unbelievable coincidence in the early universe to achieve such precision. Inflation stretches space so much that any initial curvature gets flattened out, just as blowing up a balloon makes a small patch look flatter and flatter. But again, this flattening is a change in internal geometry, not a movement into external space. A balloon expands into the air around it. The universe does not. Inflation uses the balloon as an analogy for the effect, but not for the mechanism. The mechanism is the evolution of the metric that defines distances inside spacetime. With the right energy conditions, those distances increase exponentially and no outside region plays any role. People often imagine inflation as a gigantic explosion, but this picture fails in almost every way. Explosions occur within space and push material outward. Inflation involves no pushing. During inflation, the density of the universe remained roughly constant. More space appeared, but the amount of energy per unit volume didn't dilute the way it does in ordinary expansion. This means the universe didn't spread out into emptiness. It simply scaled itself up. You can't even describe the growth using the usual ideas of speed or velocity because distant points weren't moving through space. Space was changing between them. That's why inflation allows expansion faster than the speed of light without violating relativity. Nothing traveled superluminally. The speed limit applies to motion in space, not to the behavior of space-time itself. One of the most striking consequences of inflation is that it created regions of the universe that we will never see. The speed at which space expanded was so extreme that some distances grew faster than light could cross them, permanently locking them out of causal contact. This means the observable universe, everything we can detect, is only a tiny piece of the much larger structure that inflation produced. But this larger structure still doesn't require an outside. It's just more space-time, vast stretches of it. Inflation doesn't embed the universe inside anything else, it makes more universe internally. Another important point is that inflation ended, but not everywhere at once. In most models, inflation is a process that naturally continues in some regions while stopping in others. Where it stops, a universe like ours forms and begins the slower, more familiar expansion we observe today. Where it continues, space-time keeps accelerating away from itself so rapidly that new bubble-like regions form, each with different initial conditions. This is where some people get the idea of a multiverse, but as explained earlier, this doesn't create a surrounding container. It simply extends space-time in a complicated patchwork way. Each bubble is a region of space-time with its own internal geometry evolving according to its own energy distribution. None of the bubbles expand into a higher void. They all reside within the same continuous space-time structure. Inflation also helps explain why large structures, galaxies, clusters, superclusters, look the way they do. Tiny quantum fluctuations in the very early universe were stretched to cosmic scales during inflation. These fluctuations seeded the small density variations that later collapsed into galaxies. That entire process occurred because inflation magnified the initial tiny irregularities. But those fluctuations weren't sitting in some background theatre. They were patterns in the fields that defined space-time. Inflation magnified patterns, not objects moving into emptiness. Some people ask whether inflation creates new space or reveals space that was already there. This question comes from applying everyday intuition to something that doesn't obey everyday rules. Inflation didn't reveal anything. It didn't expose pre-existing room. It created additional space-time in the only sense the word create makes sense here. The metric evolved so that more volume existed. This isn't like opening a folded map. It's like every inch of the map expanding while remaining the entire territory. There's no external geography. The success of inflation isn't measured by philosophical neatness, but by concrete predictions. It predicted the near flatness of the universe. It predicted the specific pattern of temperature variations observed in the cosmic microwave background. It predicted a specific distribution of density fluctuations that eventually formed galaxies. All of these predictions were later confirmed. None of them require a spatial exterior for the universe. They require only that space-time behave according to general relativity, and that certain energy conditions existed in the early universe. The mechanisms that drive inflation are internal, not external. The deeper you go into inflation, the more obvious it becomes that the question, what did it expand into, is misplaced. Inflation describes a change in the internal geometry of space-time, not a motion through an environment. Even the idea of an edge doesn't make sense here. If you follow the math backward, inflation erases edges by stretching them away. If you follow the math forward, the edges of different regions become unreachable because expansion outpaces causal communication. Inflation makes the early universe enormous without giving it a boundary to push against. So inflation, this dramatic, powerful, universe-shaping event, reinforces the same point we've seen again and again. Expansion, even at its most extreme, doesn't behave like familiar growth inside a surrounding container. It's geometry changing, not objects relocating. Whether in the calm expansion we see today or the violent surge of the earliest moment, space-time never expands into anything. It simply becomes more of what it already is. When people hear that the universe is expanding, it's natural to picture new space appearing at the edges, as if the cosmos has a perimeter and that boundary is getting pushed outward. But that picture comes from everyday experiences with things like balloons, puddles, and soap bubbles, objects that grow by increasing their surface area in a larger environment. The universe doesn't behave that way, and expansion doesn't resemble any familiar process happening inside a container. So the question, is new space being created, needs a careful answer because the word create carries assumptions that don't fit cosmology. To understand what actually happens, we have to look at how physicists define space, distance, and geometry in the first place. One of the biggest conceptual shifts in general relativity is that space isn't treated as a material substance. It's not a gas you can pump more of into a region or a fabric you can weave additional patches onto. It's a set of relationships, distances, intervals, and connections between events. The universe expands because those relationships change over time. The metric, which is the mathematical rule that tells you how far apart 2 points are, gradually shifts. When cosmologists say space expanded, what they really mean is distances between unbound objects increased according to the evolution of the metric. That's a mouthful, and no one talks like that in everyday life, but it's the accurate description. You don't add new stuff called space, you change the distances that define the geometry. This is easier to understand if you think about a coordinate grid rather than a physical substance. Imagine a graph drawn on a rubber sheet. The lines on the graph represent coordinates. If you stretch the sheet, the squares on the grid grow. They cover more area. But you haven't glued extra material onto the edges. You've changed the spacing of the lines. The grid didn't gain new squares in the sense of acquiring something external. Each square simply became larger. The universe works in a similar way. The coordinates that describe distances stretch with time, and the total volume increases even though nothing is being inserted from outside. However, the rubber sheet analogy can also be misleading if you take it too literally. The sheet expands into the surrounding air. The universe doesn't. The analogy is only useful for visualizing internal stretching, not for picturing an external environment. That's why cosmologists often say that space comes into being between distant objects, but they don't mean it in the philosophical sense. They mean the separation between objects grows. New spatial volume appears because the metric evolves, not because something was added at a boundary. This distinction becomes clearer when you picture the universe not as an object, but as a set of measurable distances. If the distance between two galaxies doubles, the volume of the region between them increases. You could describe that as more space existing today than yesterday, but nothing was produced like a factory product. It's just a natural result of how the geometry changes. Expansion is something space-time does, not something done to space-time. Where people get confused is with the idea of conservation. In everyday life, if something grows, it comes from somewhere. A balloon needs air, a person needs food, a fire needs fuel. We're used to things expanding by consuming resources, so when the universe expands, it's easy to ask, what resource is being consumed to make extra space? But this question assumes a material substance that doesn't exist. Space isn't made of anything that needs to be replenished. The expansion is described entirely by the equations of general relativity. The geometry can change without an external input because geometry isn't a substance, it's a structure. This also explains why expansion doesn't violate any conservation laws. Conservation of energy is tricky in general relativity, especially on cosmic scales, because the total energy of the universe isn't defined the same way it is in Newtonian physics. You can't add up all the energy in the universe and store it as a fixed number. In fact, in an expanding universe, energy densities change in ways that seem non-conservative from a classical perspective, especially when dark energy enters the picture. But this isn't a glitch, it's a feature of how general relativity works. Energy conservation in the traditional sense applies to systems where the geometry is constant over time. In an expanding universe, the geometry itself evolves, so the old rules don't apply globally. Locally, where space-time behaves roughly like flat space, energy is conserved normally. But across the universe as a whole, the bookkeeping isn't that simple. Another common question is whether space is created uniformly everywhere, or whether it appears in some preferred locations. The answer is that expansion happens uniformly on large scales, not because new space forms in particular zones, but because the metric changes everywhere. Galaxies far apart feel this change more strongly because there's more distance for expansion to act on. Nearby objects barely notice it. A galaxy cluster a few megaparsecs across doesn't expand internally because gravity holds it together. Expandable distance only shows up where gravity and other forces are too weak to counteract the stretch. But that doesn't mean expansion is localized. It's a global change in geometry that reveals itself only where nothing fights it. Think of it like a weak force pulling very lightly everywhere. Objects that are strongly bound don't respond, but unbound objects do. This helps explain why expansion feels so abstract. You can't conduct a local experiment inside your house, solar system, or galaxy that directly measures cosmic expansion. Those scales are too small and binding forces are too strong. Expansion is only obvious across millions or billions of light years, where gravitational influence fades and objects are essentially free to follow the geometry. This is another reason people imagine expansion as something being added at the edges. We don't see it happening around us, so it's tempting to imagine it happening somewhere else, like at the boundary of the universe. But there is no boundary. Expansion isn't a location-based process, it's a scale-based process. Another way to think about new space is through the idea of co-moving coordinates. In cosmology, co-moving coordinates refer to positions that expand along with the universe. Two galaxies in co-moving coordinates keep their coordinate distance fixed even as their physical separation grows. This is a powerful way to see that expansion doesn't depend on objects moving or space being created. The coordinates stretch. The scale factor, the number that translates coordinate distance into physical distance, changes with time. When the scale factor increases, all co-moving distances convert into larger real distances. Volume increases because the scale factor multiplies space. Nothing is added. Nothing flows in. The mapping between coordinates and distances changes. At this point, it's natural to ask whether space creation might apply differently, depending on whether the universe is finite or infinite. But oddly enough, the answer is the same in both cases. If the universe is infinite, then an infinite amount of space gets more infinite over time. That sounds bizarre, but mathematically it's straightforward. Infinity isn't a number, it's a description of a property. An infinite universe with larger separations between co-moving points is still infinite. You don't need to create an edge or feed it new material. The metric stretches. If the universe is finite but unbounded, like a three-dimensional version of the surface of a sphere, expansion simply makes the same unbounded region larger. You don't need an outside because a finite, unbounded shape has no exterior. You don't need to create anything at a border because there is no border. So does expansion create new space? The honest answer is, it depends what you mean. If by create you mean produce something material, then no, it doesn't. If you mean does the amount of spatial volume increase over time? Then yes, it does, because the metric evolves. But that increase doesn't imply that anything is added from outside. The geometry changes internally and physical distances grow. The universe gains volume in the same way a coordinate grid gains area when the spacing between lines increases. You don't add squares, the existing ones get larger. This is where the original question, into what is it expanding, dissolves. Expansion doesn't need a surrounding emptiness because expansion doesn't introduce anything new in the usual sense. It modifies the relationships that define the interior. The universe isn't a thing with walls, it's a system of distances and intervals that evolve. More space appears only because the rule that sets distances changes. And that rule doesn't rely on any external room to expand into. It relies only on the state of the universe itself. Dark energy enters the story when astronomers realize that the universe isn't just expanding, it's expanding faster over time. This discovery in the late 1990s changed cosmology in a way few findings ever have. Before then, everyone expected gravity to slow expansion down. Maybe the universe would expand forever, but decelerate, or maybe it would eventually stop and reverse. Either way, the logic was straightforward. Matter has mass, mass creates gravity, and gravity pulls things together. Expansion should weaken over time. But that isn't what the universe does. Instead, distant galaxies are receding faster now than they were billions of years ago. The expansion is accelerating, and the force behind that acceleration was given a name: dark energy. The term dark energy doesn't describe a mysterious substance floating around. It's a label for whatever is causing this acceleration. And the key feature of dark energy is that it behaves nothing like ordinary matter or radiation. Matter thins out as the universe expands because it's spread across a growing volume. Radiation thins out too, and its energy decreases as its wavelengths stretch. But dark energy doesn't dilute. Its density stays roughly constant as space expands. That single fact has enormous consequences for the question we're dealing with, because it means that expansion isn't driven by something pushing from outside. It's driven by something built into space-time itself. If you imagine the universe as a system of distances defined by geometry, dark energy changes how that geometry evolves. Instead of gravity slowing the growth of those distances, dark energy makes them grow faster. You can think of it as a property of space-time that resists compression and encourages expansion. It's not a pressure in the traditional sense, but mathematically it acts as if space-time has a kind of negative pressure, one that counteracts the pull of gravity on very large scales. This negative pressure alters the metric the same way mass and energy do in general relativity, but it alters it in a way that leads to acceleration instead of deceleration. A common analogy is to imagine stretching a rubber sheet. Gravity behaves like objects pulling on the sheet, creating dips that draw nearby material inward. Dark energy behaves differently. It acts like a subtle, uniform tendency of the entire sheet to expand itself. There's no central point, no edge where the stretching begins. The whole sheet changes at once. But, like all analogies, this one can mislead if taken too literally. A rubber sheet still expands into air. The universe does not. The analogy is only meant to show that dark energy operates everywhere rather than pushing from one direction or another. Dark energy's effect is most visible on the largest scales, hundreds of millions of light years and beyond. Gravity holds galaxies together. It holds clusters together. It shapes superclusters. But when you step back far enough, the pull of gravity weakens, and the influence of dark energy becomes dominant. On those scales, it's the main thing shaping the future of the universe. This is why galaxy groups bound tightly by gravity will stay bound indefinitely, but galaxies separated by great distances will accelerate away from one another forever. This uniform behavior explains another crucial point. Dark energy doesn't accumulate anywhere. It isn't something that collects at boundaries or forms pockets. If you doubled the size of the universe, you'd double the amount of dark energy because it has constant density. This is why expansion speeds up. There's always more space, and that new space has the same amount of dark energy per volume as before. More space means more dark energy-driven expansion. It's a feedback loop built into the geometry itself, not a process happening at edges. And because there are no edges, there's nowhere for dark energy to push into. A lot of confusion comes from the name energy, which makes people imagine a physical substance. But dark energy is most accurately described as a property of space-time. It could be a cosmological constant, a fixed value built into the structure of the universe. Or it could be something more dynamic, like a field that changes over time. Scientists don't know the exact form yet, but whatever it is, it affects the universe everywhere, not in a directional or boundary-based way. Its influence doesn't come from an external cause. One of the clearest illustrations of this is the fate of light traveling through the universe. As light moves across expanding space, its wavelength stretches, losing energy in the process. This redshift increases with distance, but in an accelerating universe, the stretching accelerates too. There comes a point where distant galaxies move away so fast because the space between us accelerates in its expansion that their light will never reach us, no matter how long we wait. This isn't because they've crossed a physical wall or boundary, it's because the geometry changes too rapidly for their signals to keep up. Dark energy is the reason those regions slip permanently out of view. And this brings us to the crucial connection with the original question. If the universe is expanding faster and faster, what is it expanding into? Dark energy reinforces the same answer we've been seeing all along. It isn't expanding into anything. The acceleration happens internally. More distance appears between unbound regions because the metric evolves in a particular way. The effect of dark energy is baked into this evolution. It doesn't require space outside the universe to act upon. It doesn't create new room in which the universe grows. It changes the behavior of the room the universe already is. Another way to see this is by considering how the total energy in a region of the universe behaves. If you expand a region of ordinary matter, its density drops and the total energy within that region decreases. But if you expand a region filled with dark energy, the total energy increases because the density stays the same but the volume increases. This looks like energy appearing, which seems odd unless you remember that energy conservation in general relativity isn't global. When space-time changes over time, the usual conservation rules don't apply in the simple way they do in everyday physics. Dark energy's behavior fits perfectly within the framework of general relativity without requiring an external supply. There's no empty space outside pumping energy in. There's no reservoir. The geometry evolves, and the energy budget changes with it. This outlook becomes even more striking when you consider long-term projections. As the universe continues accelerating, distant galaxies will slip beyond our horizon. Anything not gravitationally bound to the local group will eventually be so far away that its light will never reach us. But this doesn't mean space is growing into something. It means the geometry is shifting so quickly that connections fade. The distances grow faster than signals can bridge them. Dark energy accelerates the divergence of regions, but never pushes the universe outward into a surrounding void. In the far future, if dark energy remains constant, the expansion will approach exponential growth again, similar to inflation but vastly slower. But even in that distant era, no boundary forms. No new exterior reveals itself. No sign appears that the universe is moving through a background. Everything that happens occurs within the evolving network of distances that make up space-time. So dark energy, rather than hinting at an outside or pushing from beyond, reinforces the core principle of modern cosmology. Expansion is a change in geometry, driven internally. The accelerating growth of space doesn't require a container. It only requires the laws that govern space-time itself. Higher dimensions are one of the easiest places for the imagination to wander when trying to understand the universe's expansion. If the universe isn't expanding into anything, then maybe, just maybe, it's expanding into a higher dimensional space, like a bubble inflating inside a larger arena we cannot see. This idea shows up all the time in pop culture and even in some scientific metaphors. It feels like it solves the problem. If our three-dimensional universe sits inside a higher dimensional bulk, then expansion might seem like it finally has a place to go. But while higher dimensions make for great imagery, they don't actually solve the core question unless you redefine what universe means. And in most models, they aren't needed at all. To understand why, it helps to look at how these ideas appear in physics and how they often get misunderstood. When cosmologists talk about extra dimensions, they're usually referring to theories like string theory or certain versions of inflation that postulate dimensions beyond the familiar three of space and one of time. But these extra dimensions are not like ordinary directions you could point to. In many models, they're compactified, curled up so tightly that they're effectively invisible. Even if you somehow zoomed in on them, which we currently don't know how to do, they wouldn't exist as a place the universe expands into. They're built into the mathematical structure of space-time, not sitting outside it like additional territory. Expansion still happens internally because the larger-scale geometry changes. One of the most common sources of confusion is the image of a balloon as a model of the expanding universe. When you look at the balloon, it expands into the surrounding air. So it's easy to conclude that the universe must behave the same way, with the balloon's surface representing our universe and the space around the balloon serving as a higher dimensional container. But this is just an analogy. The only part that maps onto real cosmology is the surface of the balloon, not the air around it. In the analogy, the inhabitants live on the two-dimensional surface. They don't know about the third dimension. They see distances on their surface growing even though they aren't moving across it. That part captures how expansion works. But the embedding space, the air the balloon grows into, is not part of the analogy. It's only there because we, as three-dimensional creatures, need something physical to hold the balloon in our hands. Mathematically, a curved surface doesn't need to be embedded in higher dimensions. It can be defined completely by its internal geometry. The same is true for the universe. Something similar applies to modern higher dimensional theories. They can describe space-time as having more dimensions than we can perceive, but those extra dimensions don't act like empty arenas waiting to be filled. In many models, the higher dimensions are part of the mathematical framework that shapes the laws of physics within our three-dimensional world. They influence particle interactions, symmetries, and early universe behavior, but they don't create a surrounding volume for the cosmos to expand into. Even in scenarios where our universe is described as a brain inside a higher dimensional space, the expansion we observe is not motion through that space. It's a change in the brain's internal metric. Distances within the brain increase. The extra dimensions themselves remain something that doesn't function like a place. There's another subtle point. Adding higher dimensions doesn't actually fix the conceptual problem of outside. If you place our universe inside a 5-dimensional or 10-dimensional space, you've simply expanded the definition of universe. That higher dimensional structure becomes part of the totality of what exists. You haven't created a true outside, you've just enlarged the inside. This mirrors the earlier point that if something exists, obeys laws and interacts, then it already belongs to the universe by definition. You can't escape the concept by adding dimensions. You can only change what universe includes. Physicists also use higher dimensions in certain inflation models, particularly those involving eternal inflation, where individual bubble-like regions form within a larger inflating background. People often imagine these bubbles floating in a giant extra-dimensional foam. But the background in these models isn't a container. It's just more space-time obeying the same rules. A bubble universe doesn't expand into that space. Its expansion is still internal. The bubble walls don't move outward into an empty void. Instead, the distances inside the bubble grow because the geometric rules inside it evolve. The background inflates independently according to its own dynamics. Nothing about the bubble universe's growth depends on external room. This leads to a deeper insight. Higher dimensions can help generate the conditions that cause expansion, but they don't provide a place for expansion to occur. They can produce energy fields that shape the early universe. They can influence the geometry that inflation magnifies. They can change the behavior of particles. But they don't turn the universe into a balloon inside a space. Higher dimensional theories don't add a physical outside any more than adding more numbers adds a place beyond the number line. They add structure, not territory. A good way to tell whether a higher dimensional model is solving the expanding into what question is to ask whether it introduces a true external region that remains outside the universe by definition. In every serious scientific model, it doesn't. Either the higher dimensions are part of the universe, or they're not meaningful in the sense of providing a location. If they're part of the universe, then expansion still happens within them, not into them. If they don't interact or produce measurable effects, then they might as well not exist physically. Even the idea of brain collision models where universes could interact doesn't imply an external arena. If two brains interact, that interaction is part of the total physical system, meaning it's part of the universe. Nothing is outside. What changes is just how space-time behaves. These models don't introduce a cosmic container. They introduce more complicated ways for space-time to operate internally. So, higher dimensions can change the story of how the universe behaves. They can alter the shape of physical laws, influence the early universe, and even introduce new mechanisms for inflation. But they don't give the universe a surrounding backdrop. Expansion remains a change in the internal geometry, regardless of how many dimensions that geometry has. Whether spacetime has 4 dimensions or 11, expansion describes how the distances within that spacetime evolve. It doesn't describe motion through a larger realm. That's why higher dimensions, despite being fascinating and sometimes essential in advanced physics, don't solve the question of what the universe expands into. They don't create a container, they expand the mathematical toolkit, not the physical surroundings. You can add as many dimensions as you'd like, and the answer remains the same. The universe doesn't expand into anything. Its geometry changes, and that change is complete without needing an external place. A finite universe is one of the trickiest ideas to wrap your head around because the moment you hear the word finite, your mind immediately attaches another idea to it. Bounded. If something has a finite size, you expect it to have edges, borders, or a surface where the inside stops and something else begins. That's how nearly everything in everyday life works. Rooms, lakes, planets, boxes, balloons. So when cosmologists say the universe might be finite, the next question comes almost automatically. If it has a finite size, what lies beyond its boundary? And if the universe expands, is that boundary pushing into something? The answer is that a finite universe doesn't require edges, and because it doesn't have edges, it doesn't expand into anything. To understand how that works, you have to step away from everyday examples and think more abstractly about geometry. The key idea is that something can be finite, yet unbounded. The surface of a sphere is the classic analogy. The surface has a finite area, but there's no edge. You can walk around the surface forever without falling off or finding a border. Every direction leads somewhere, and if you keep going long enough, you eventually return to where you started. The surface is finite because its area is limited, but it's unbounded because it has no boundary. This kind of geometry isn't just a mathematical curiosity, it's a realistic possibility for the overall shape of the universe. In 3 dimensions, the equivalent would be a closed, finite, unbounded shape, something like a 3-dimensional sphere called a hypersphere. You could travel in any direction indefinitely and never hit an edge, even though the total volume would be limited. The moment you picture a hypersphere, though, your imagination may sneak in the idea of an embedding space, a higher dimensional arena that the hypersphere curves through. But that extra space isn't necessary. Mathematically, a finite, unbounded geometry doesn't need to exist inside anything. It can be described entirely by the distances between points within it. When cosmologists say the universe might be finite, that's what they mean. The three-dimensional geometry curves back on itself in a way that's complete and self-contained. If you picture it as sitting inside a four-dimensional space, that's only a visualization tool, not a physical requirement. The embedding space isn't part of the actual model. The internal geometry stands on its own. Once you accept that a finite universe doesn't need boundaries, it becomes clearer how such a universe can expand without expanding into a surrounding region. Expansion simply means that the internal distances grow over time. On a two-dimensional sphere, this would look like the radius increasing. You'd see every point drift away from every other point, not because the sphere pushes outward into anything, but because the surface stretches. The surface area increases as a result of that stretching. The same applies to a three-dimensional finite universe. The scale factor, the multiplier that converts coordinate distances into physical distances, increases, causing the internal volume to grow. Nothing gets added to the outside. The structure just scales. This also shows why expansion has no center in a finite universe. If the universe were finite with a literal center, that center would be an absolute reference point. Distances from it would behave differently. We would detect anisotropies in every direction, some form of preferred orientation. But all observations show that expansion looks the same in every direction from every location we can check. That's exactly what you'd expect from a finite, unbounded geometry. There is no special place from which expansion originates. Every point sees every other point moving away, because the geometry itself changes uniformly. Now consider what happens on a smaller scale inside such a universe. Expansion doesn't tear apart planets, stars, or galaxies. Their internal gravity dominates to such a degree that expansion becomes irrelevant. The stretching effect shows up only on scales where gravity is weak compared to the overall evolution of space-time, distances of millions or billions of light-years. This is true whether the universe is finite or infinite. The local physics doesn't depend on global shape. The structure of the universe on the largest scales sets the stage for expansion, but the expansion doesn't alter the fact that gravitational systems stay intact. If the universe is finite, another natural question arises. Could we eventually detect its finiteness? In principle, yes. A finite universe could produce repeated patterns in the cosmic microwave background if light wraps around the cosmos and reaches us from multiple directions. Scientists have searched for these patterns, like matching temperature rings or repeated distortions, but so far haven't found convincing evidence. That doesn't rule out a finite universe. It just means that if it is finite, it's probably large enough that light hasn't wrapped around far enough for us to detect the repetitions. A finite universe also raises the question of what its size means. There isn't a physical wall. The size depends on the scale factor, the current value that defines how big distances are at the present moment. As the universe expands, the scale factor increases and the total volume of the finite cosmos increases. But again, this doesn't imply that the universe enlarges into an external space. It means the metric, the rule that sets distances, changes. A finite universe grows the same way a balloon's surface area increases, except the balloon analogy misleads if you start imagining the balloon floating in a room. The surface area grows because the geometry changes, not because the balloon has external room to occupy. Another subtle point is that expansion doesn't require the universe to maintain a fixed finite shape. The geometry can evolve over time. A finite universe doesn't have to remain a perfect hypersphere. It can have more complicated curvature that changes with cosmic evolution. The key feature is the absence of boundaries, not the exact curvature pattern. No matter how the geometry shifts, as long as it remains unbounded, expansion remains an internal process. It's also important to note that finite does not mean small. If the universe is finite, it could still be enormously larger than our observable horizon. We might inhabit a region that looks flat locally, even if the global geometry curves. The observable universe, everything we can see, would be a tiny patch of the entire structure. Whether the universe is finite or infinite doesn't change how we measure expansion on observable scales. We observe galaxies receding, not because they're moving toward edges, but because the metric changes everywhere. In the end, the concept of a finite universe doesn't challenge the principle that expansion doesn't need an outside. Finite cosmologies simply give another way to see it. Expansion increases internal distances, magnifies the volume, and reshapes the geometry without requiring any external region. A finite universe can grow forever without ever being inside something larger because its geometry is complete in itself. If the universe is infinite, the idea of expansion becomes even stranger at first glance. When something is already infinite, what does it mean for it to grow? Infinity doesn't get bigger in everyday life. An infinite line stays infinite no matter how far you stretch it. And that's actually the key. The universe doesn't become more infinite. It stays infinite. What changes is the spacing between things within that infinite structure. Expansion isn't about creating new territory at the edge of infinity. It's about scaling distances everywhere at once. Imagine an infinite grid with a dot at each intersection. If the grid stretches, every dot moves farther from every other dot. The grid remains infinite the entire time. The number of intersections remains infinite. The extension in each direction remains infinite. But the spacing between the dots grows. That's essentially what cosmologists mean by expansion in an infinite universe. The expansion changes the metric, the rule that assigns physical distances, not the overall extent. Infinity doesn't need new space added around the edges because it doesn't have edges to begin with. This is why expansion in an infinite universe has no center. If the universe were stretching outward from a central point, then distances would behave differently depending on where you stood. But in an infinite universe with uniform expansion, every point sees every other point moving away. Observers separated by billions of light years get the same picture. This uniformity is a core part of what cosmologists call the cosmological principle, the idea that on the larger scales the universe looks roughly the same everywhere. Infinite or not, uniform expansion lines up with that principle perfectly. Once you understand that expansion doesn't add new space at the edges, it becomes easier to make sense of how an infinite universe evolves. What changes is the scale factor, the number that tells you how large distances are at a given cosmic time. If the scale factor doubles, every large-scale distance doubles. The universe doesn't grow from infinity to something larger than infinity. It simply becomes a version of infinity with different spacing. That leads to a natural follow-up question. If the universe is infinite, did it start infinite? According to the standard cosmological model, yes, that's one valid possibility. The Big Bang doesn't describe an explosion at a point. It describes an early state where the scale factor was smaller everywhere. An infinite universe could have existed from the beginning but packed into a much higher density configuration. Every region was closer to every other region, even though the total extent was unbounded. When the early universe expanded, the density dropped, the temperature dropped, and structures began forming, but the infinity never disappeared or reappeared. It remained infinite the whole time, and that's one of the big differences between how people imagine the Big Bang and what the equations actually describe. The Big Bang wasn't a moment when a finite amount of matter burst outward into emptiness. It was a moment when the scale factor was extremely small and increasing. If you zoom in far enough to the earliest moments we can describe with confidence, the distances between points shrink towards zero. But the number of points can still be infinite. Infinity can be compressed. It doesn't need a boundary to squeeze against. The expansion of an infinite universe also fits naturally with the way we observe galaxies. When astronomers measure redshift, the stretching of light caused by the expansion, they find that galaxies twice as far away move away at roughly twice the speed. Galaxies 3 times farther move away at 3 times the speed, and so on. That relationship is exactly what you'd expect in a uniformly expanding infinite space. There's no preferred center. Every point participates in the same stretching. Another interesting consequence is that in an infinite universe, there are always more galaxies beyond any distance you name. Expansion doesn't thin them out to the point of emptiness, they just keep getting farther away. The observable universe stays finite because light has a finite speed and the universe has a finite age, but the total number of galaxies beyond that horizon could be infinite. Expansion ensures that most of those galaxies will always remain beyond reach. Light from many of them will never get here because the space between us grows too quickly. In an infinite universe, expansion doesn't just separate galaxies, it creates permanent communication barriers. Then there's the future. If the universe is infinite and expansion continues accelerating under the influence of dark energy, those separations grow faster and faster. Over extremely long timescales, distant galaxies fade from view one by one. Not because they cease to exist, but because space stretches so quickly that their light can't bridge the increasing gap. Eventually, only the galaxies gravitationally bound to ours remain visible. An infinite universe becomes increasingly isolated for any given observer. But still, at every moment in time, the total extent remains infinite. Expansion never adds new regions. It only increases the distances within the existing structure. One of the biggest conceptual hurdles people face with an infinite universe is imagining how something infinite can evolve meaningfully. It helps to remember that infinity is not a physical object. It's a description of extent. Expansion doesn't manipulate infinity itself. It manipulates the scaling of distances. You can take an infinite line, stretch it by any factor you want, and it's still infinite. The stretching is a real physical change, even though the infinity stays the same. Cosmology works the same way. Expansion is a physical process that changes how matter and light behave, even though the universe doesn't acquire more infinity. This also highlights why expansion doesn't need external space. The entire structure is self-contained. There's no boundary to cross, no empty external region waiting to be filled, no hole of nothingness that the universe pushes into. An infinite universe is simply a dynamic geometry, one where distances evolve according to the laws of general relativity. Expansion is a change in the geometry, not a movement outward. In summary, if the universe is infinite, expansion is not about increasing the size of infinity. It's about increasing the distance between points within an already unbounded structure. The universe doesn't expand into anything because its geometry doesn't require an outside. Infinity stays infinite. What changes is the scale of everything inside it. When you follow expansion all the way forward, you end up in a landscape where everyday intuition fails almost completely. The universe becomes quieter, darker, and more stretched out than anything we can relate to. But the key point is that none of this relies on the universe expanding into something. Everything that happens in the far future comes from what expansion does within the universe, not outside it. The basic trend is simple. The expansion that's happening today is speeding up. Galaxies aren't just drifting apart. Each decade, the rate at which space stretches gets a little faster. That acceleration comes from dark energy, the name we give to whatever's causing the expansion to pick up speed instead of slowing down. If this acceleration continues indefinitely, the universe heads toward a future where the large-scale structure keeps spreading out until distant galaxies vanish from view. It's not that they stop shining. Their light just can't reach us anymore because the space between us outgrows the ability of light to cross it. Over the next tens of billions of years, that process accelerates. The galaxies that are already far away slip beyond our cosmic horizon one by one. Their light takes longer and longer to reach us until eventually it never does. The universe doesn't lose galaxies. Communication simply breaks down. From our point of view inside the Milky Way and its future, merged neighbor Andromeda, it begins to look as if we occupy an island of stars floating in utter darkness. The true universe is still out there, but expansion hides nearly all of it. Inside those gravitationally bound islands, life goes on for a while. Stars continue to burn, planets survive, and the local environment stays intact. Expansion doesn't affect systems held together by gravity or electromagnetism. But those internal clocks eventually run out. Over hundreds of billions of years, stars burn through their fuel. Bright, short-lived stars go first. Longer-lived stars follow. Eventually you're left with stellar remnants, white dwarfs, neutron stars, and black holes. These remnants cool and fade. New stars stop forming. The night sky, even inside the remaining galaxies, becomes dim and sparse. As time moves further ahead, trillions of years, black holes start to dominate what's left. They slowly evaporate through Hawking radiation, an incredibly slow process, but one that eventually wins. A black hole with the mass of the Sun takes around 10 to the power of 67 years to evaporate. Larger ones take longer, but even those giants have an expiration date. After unimaginable spans of time, every black hole gives up its mass and disappears in a final, faint burst of energy. At that point, the universe is extremely dilute. Matter is spread so thin that particles can go vast distances without interacting with anything. The cosmic temperature drops extremely close to absolute zero. Expansion continues, not because there's a destination, but because the dynamics built into space-time keep doing what they've always done. Stretch distances according to the amount of dark energy present. This long-term picture is often called heat death, but the name is a bit misleading. It doesn't mean the universe gets hot. It means the universe reaches a state where no meaningful energy gradients exist. You need gradients, differences in temperature, density, or pressure, for anything interesting to happen. Stars shining, planets forming, chemistry operating, biological processes functioning. In the far future, those gradients vanish. Everything approaches uniformity. No direction is special. No region is high energy compared to another. The universe becomes a quiet, cold bath of sparse particles and radiation. Notice what never appears anywhere in this story. An outside. The universe never expands into a larger container. The heat death scenario unfolds entirely inside the universe itself. The distances involved become enormous, but those distances don't push into anything external. It's like watching the numbers on a ruler grow larger without the ruler touching any new territory. The story is internal from beginning to end. There are alternate possibilities too. In some theories, dark energy might not stay constant. If it grows stronger over time, expansion could accelerate so violently that even galaxies, stars, and atoms eventually get pulled apart, a scenario known as the Big Rip. In others, dark energy might weaken someday, allowing expansion to slow or even reverse. Those ideas are more speculative and depend on physics we don't fully understand yet. But even in those more exotic scenarios, expansion still doesn't require an external region. Whether the universe smooths out, tears apart, or cycles through new phases, every possibility plays out within its own geometry. Nothing relies on external space. So the far future of the universe, however it unfolds, remains an internal story. The universe changes from within. Galaxies drift out of view, stars fade, black holes evaporate, and space-time keeps stretching. Nothing expands into an outside region because the universe doesn't have an outside in the first place. Expansion is the evolution of space-time, not motion toward a surrounding void. Now, by this point, the pieces are all on the table, but the topic is so counterintuitive that some misunderstandings tend to hang on even after you've seen the full picture. These misunderstandings mostly come from trying to apply everyday experience to something that doesn't behave like anything we encounter day to day. The easiest way to clear them up is to revisit the most persistent ones directly and lay out why they don't match what cosmologists mean. The first is the classic idea that the universe must be expanding from somewhere. If you imagine a firework exploding, you picture fragments flying outward from a central point. It's a natural comparison, but it creates the wrong mental frame. In the real universe, every point sees every other point moving away on large scales. There's no preferred location where expansion started. If there were a center, galaxies on one side of the universe would behave differently from galaxies on the other. Their speeds, temperatures, clustering patterns, and the structure of the cosmic microwave background would all reveal a directional bias. But when scientists map the sky, the data is remarkably uniform. That uniformity is exactly what you get when space itself expands evenly everywhere instead of pushing outward from a single spot. A close relative of that misconception is the idea that the universe must have an edge, a frontier, past which there's nothing. If there were such an edge, you'd expect it to behave like a boundary. Light reaching it might reflect or stop. Matter approaching it might feel different gravitational effects. None of this shows up in what we observe. Instead, the observable universe is surrounded by more universe that lies beyond our current horizon. The fact that we can't see past that horizon doesn't mean there's a wall there. It means light hasn't had enough time to reach us from those regions. The boundary of visibility is set by time and the speed of light, not by a physical edge. Then there's the very common belief that the Big Bang describes an explosion in pre-existing empty space. This misconception is so widespread that it shapes how many people think about cosmology long before they encounter a more precise explanation. But the Big Bang wasn't a blast of matter into emptiness. It was the moment when the universe entered a hot, dense, rapidly expanding state. Space didn't exist before that moment in any meaningful physical sense. Time didn't either. Asking what the universe expanded into at the Big Bang is like asking what lies north of the North Pole. The question feels sensible, but only because we're trying to extend concepts past where they apply. The Big Bang describes the early behavior of space-time, not a burst in a larger arena. Another misconception is that expansion must stretch everything, including atoms, rocks, planets, and people. But expansion is incredibly weak on small scales. The only reason it dominates on cosmic scales is that large regions of space between galaxies aren't strongly held together by gravity or other forces. On smaller scales, local forces win easily. Your body doesn't expand. Earth doesn't expand. The solar system doesn't expand. Even galaxies don't expand. The expansion of the universe becomes noticeable only when you look at distances so large that no internal forces bind the matter together. A tied-in misunderstanding is the idea that if the universe expands, then distant galaxies must be moving through space. But cosmologists are careful with language here. Most of the redshift we observe, especially for the most distant galaxies, comes not from motion through space, but from space itself stretching. Galaxies are carried apart because the metric changes. When you see a galaxy with a huge redshift, that doesn't mean it's racing away from you like a rocket. It means the light it emitted has been stretched while traveling through expanding space. People also frequently assume that if the universe is infinite, expansion makes it more infinite. Or if it's finite, expansion makes it break its boundaries. Both versions come from comparing the universe to objects in everyday experience. But the universe doesn't behave like an object. Infinity doesn't change when distances scale, and a finite universe with no boundary doesn't need new territory to grow into. Expansion changes how distances behave, not the overall structure that distances are measured within. There's also the idea that if the universe is expanding, we should be able to find a spot where it isn't. But that's not how cosmic expansion works. Expansion is baked into the geometry. It's not a wind you can outrun or a motion you can step outside of. If you took a spaceship and flew across billions of light years, you'd still see distant galaxies receding. No matter where you go, the pattern holds. You can't get closer to the origin point because there isn't one. One last misunderstanding shows up when people hear that the observable universe has a radius of about 46 billion light years. They sometimes take that radius as the size of the whole universe. But the observable universe is limited by how far light has traveled since the Big Bang. It's a sightline limit, not a physical boundary. As time passes, more regions come into view for a while, and then, because of accelerated expansion, fewer do. The physical universe could be vastly larger than the observable one. It could be infinite. The observable horizon is just the sphere of what we've had time to see. When you line up all these misconceptions, a pattern emerges. Nearly all of them come from trying to treat the universe as an object with a shape, a location, a surface, or a trajectory. But the universe isn't an object in space, it's the framework of space itself. Distances change not because something is moving outward, but because the geometry evolves. The universe doesn't sit inside a larger region. It contains its own rules for how distances, time, and energy behave. After all the complexity, the clean answer is surprisingly simple once you strip away the intuitions that don't apply. The universe is not an object expanding into space. It's the thing that defines what space is. When cosmologists say the universe is expanding, they mean the distances between widely separated regions grow over time because the geometry of space-time changes. Nothing moves outward into an external void because there is no external void. There is no surrounding container, no outside arena, and no boundary to cross. This becomes easier to see when you remember that expansion looks the same everywhere. Every galaxy far enough away appears to drift from every other galaxy. That uniform pattern only makes sense if expansion is baked into the geometry itself. If there were an outside, the expansion would have a direction, a center, or an edge. We don't see any of those. What we do see is distance scaling, an internal reshaping of space-time. Whether the universe is finite or infinite doesn't change that logic. A finite universe can be unbounded, so it doesn't need space around it to grow. An infinite universe stays infinite as the scale factor increases. In both cases, expansion is purely internal. It changes the metric, not the extent of a container. And the Big Bang wasn't an explosion into emptiness. It was the moment space-time began in a hot, dense, rapidly expanding state. So the best working answer is this: the universe doesn't expand into anything. Expansion happens within the universe itself. As time moves forward, the geometry stretches, distances grow, and the observable horizon evolves. Everything that expands, contracts, cools, or forms does so inside a self-contained space-time with no external backdrop. When you hear the universe is expanding, think of scaling, not outward motion. Think of distances changing, not a balloon pushing into a void. Expansion is the evolution of space-time itself, and everything we observe, from redshift to the cosmic microwave background, fits that picture. No outside is needed, and nothing is missing from the model when we leave that idea behind. When we hear that the universe is expanding, our brains jump to a picture that works for everything we've ever seen. If something grows, it must be growing into something else. A balloon expands into the air around it. Dough rises by pushing into the space inside a bowl. Crowds expand by spilling into nearby streets. So it feels natural to imagine the universe pushing outward into some enormous emptiness beyond everything. But the word universe doesn't work that way. In cosmology, the universe isn't a bubble floating in a bigger space. It is space. It's the totality of distances, geometry, and time itself. Once you treat it that way, the question, what is it expanding into, turns out to be the wrong starting point, because the usual rules for growing objects don't apply when the thing growing is the fabric that defines distance in the first place. The surprising part is that expansion isn't stretching toward an external void. It's a change in the distances between things within the universe. There's no outer shell, no wall, no container, just space-time evolving from the inside out, without any outside at all. It feels intuitive that expansion must happen into something because everything you've ever seen that grows does so inside a larger environment. But the universe is not a thing in space. It's the structure that includes space. Once you loosen the assumption that expansion must be outward motion, the confusion starts to fade. Expansion is about geometry, not about pushing into emptiness. One of the biggest sources of misunderstanding is how we use the word universe. There's the observable universe, the part from which light has had time to reach us. That region has a radius, but only because time and light speed limit what we can see. Beyond that is the physical universe, everything that exists, seen or unseen. And then there's space-time itself, the geometry that doesn't sit inside anything at all. Mixing these meanings creates questions that feel profound but come from category confusion. Once you separate them, the shape of the problem becomes clearer. Expansion changes what is visible, not where the universe is located. A century ago, astronomers expected a static cosmos. That idea shattered when Edwin Hubble found that galaxies weren't standing still. They receded faster the farther away they were. That pattern wasn't random drifting, and it wasn't debris flying from a central explosion. It was the unmistakable signature of distances increasing throughout the cosmos. The discovery came from data, not theory. And as soon as scientists accepted expansion, the familiar question appeared. If space expands, what is it expanding into? Einstein's general relativity gives the answer. It treats space not as a container, but as a flexible geometry. Distances can grow even if nothing moves into anything. When cosmologists talk about expanding space, they're describing a change in the metric, the mathematical rule that tells you how far apart things are. If the metric changes, galaxies can sit still in their local coordinates and still end up farther apart. The stretching is internal. No external room is required. If you imagine the universe expanding into something, you're imagining a background stage. But relativity doesn't provide one. The universe isn't embedded in anything. There is no giant void waiting outside. The geometry defines itself. The trick is to stop imagining movement through space and start imagining changes of space. Expansion is the growth of distance, not the movement of objects into new territory. That's why we don't see a center or an edge. If expansion were outward motion into a surrounding emptiness, it would distort the universe in detectable ways. Instead, every distant galaxy recedes from every other in the same way, no matter where you look. Only an internal stretching of space-time matches the observations. The balloon analogy helps, but only if you use it carefully. Picture galaxies as dots on the surface of a balloon. As the balloon inflates, all dots move away from one another. There's no center on the surface, and the surface is finite, yet unbounded. The mistake is imagining the balloon floating in a room. The room isn't part of the analogy. The point is that distances can grow without any dot racing toward a cosmic edge. The analogy is about internal expansion, not about surroundings. People sometimes wonder why expansion doesn't stretch atoms or tear apart the solar system. That's because local forces are stronger than expansion. Gravity binds galaxies. Electromagnetism holds matter together. Expansion only dominates on enormous scales, millions of light years or more, where nothing binds distant regions enough to resist the stretching of space. You never feel expansion, and nothing nearby stretches from it. Astronomers measure expansion through redshift. As light travels through expanding space, its wavelength stretches, shifting toward red. When they compare redshift with distance, the pattern is unmistakable. Distant regions recede faster than nearby ones. That smooth pattern shows up in galaxies, supernova, gravitational lenses, and even the cosmic microwave background. It is the observational fingerprint of expanding geometry. The shape of the universe, flat, open, or closed, doesn't change the basic idea. A closed universe can expand without an outside because its geometry curves back on itself, like the surface of a sphere. A flat or open universe can be infinite and still expand because infinity can stretch without gaining new territory. Geometry sets the rules, but none of the possible shapes require an external environment. People sometimes ask whether the universe has an edge. If there were one, light and matter near it would behave strangely. But the cosmos looks smooth and uniform. The only edge we talk about is the observable horizon, the limit of how far light has traveled so far. It isn't a boundary, it's a marker of time, not space. What about the multiverse? Even if other universes exist, they aren't balloons floating in a shared container. Each would have its own space-time. Adding more universes doesn't create an outside for ours. It just adds more structures, each with its own internal rules. Before normal expansion began, the universe went through inflation, a burst of ultra-fast stretching. Even then, nothing expanded into anything. The geometry itself expanded. Inflation made the universe large compared to what came before, but it didn't occupy an external room. It simply grew in its own space-time. People sometimes say expansion creates new space, but not in the sense of adding material to the edges. Expansion changes the metric everywhere. Distances grow. There's no outer shell of newly formed emptiness. The universe doesn't bolt on new sections. It simply stretches the geometry it already has. Dark energy accelerates this stretching. It isn't a force pushing outward. It's a property of space-time that changes how the geometry evolves. Because it acts uniformly, it increases the rate of expansion everywhere, not in any direction. Again, nothing is moving into anything. Some people picture the universe expanding inside a higher dimension. That can be a useful visualization, but it isn't necessary. The equations that describe expansion work perfectly well without extra dimensions. Even if they exist, they don't give the universe an outside region. They just change the internal structure. If the universe is finite, it can still expand. A finite universe can be unbounded, like the surface of a sphere. You can travel forever without ever finding an edge. When such a universe expands, its internal distances increase, its volume grows, but it never needs an outside region to expand into. It is complete as it is. If the universe is infinite, expansion doesn't add new infinity. It stretches the existing infinity. Distances increase, but the total extent remains unbounded. An infinite grid can double its spacing and still be infinite. That's what expansion means in an infinite cosmos. In the far future, if expansion continues accelerating, distant galaxies will slip beyond our cosmic horizon. Their light will never reach us again. Over trillions of years, stars will die out, galaxies will dim, black holes will evaporate, and the universe will cool toward a quiet, low-energy state. All of this unfolds internally, with no outside environment involved. A lot of confusion clears up once you let go of the idea of a cosmic edge or a surrounding void. There is no center, no outer boundary, no explosion into space. The Big Bang wasn't an event inside something. It was the beginning of space-time as we know it. Expansion doesn't move galaxies through empty room. It stretches the distances between them. So the clean answer to the original question is this: the universe doesn't expand into anything. Expansion happens within the universe. Distances grow because space-time evolves. There's no external void, no container, no outer environment waiting to be filled. When astronomers say the universe is expanding, they mean that the geometry of space-time is stretching. If you imagine outward motion, you'll always picture a boundary or an outside that cosmology doesn't find. Expansion is the scaling of the universe's own geometry, not movement into emptiness. Subscribe.